The universe we can see is bigger than we can imagine, with maybe 2 trillion galaxies, and each of them has hundreds of billions of stars. Thanks to powerful telescopes like Kepler and the James Webb, we have already found over 5,000 planets orbiting these other stars. It seems like a lot, right? But here is the surprising thing that changes everything. Almost none of them seem to be truly good for life as we know it. We always look for liquid water, but scientists are discovering that life needs much more. It needs the right kind of star, the exact distance, a moon, to stabilize the planet, and even a strong magnetic field to protect it from dangerous rays from space. This made scientists ask themselves, could life on Earth have been just a lucky accident that happened only one single time in the entire universe? Prepare to sleep while listening to this video as we discover what makes a planet truly habitable. Subscribe to the channel, leave your like, and comment what part of the world you are watching from. Get comfortable and relax. Let's begin. Imagine staring up at the night sky, filled with countless stars, and feeling that life must be everywhere out there. But what if that feeling is wrong, and the cosmos is mostly empty of life? The universe is so immense it defies easy comprehension, with trillions of galaxies, each holding billions of stars, and many of those stars likely host planets. This sheer scale suggests a high statistical probability for life to exist somewhere, perhaps in many somewheres. Yet this same vastness introduces a profound challenge. Finding a specific planet that meets all the exacting conditions for life is like searching for a single grain of sand on all the beaches of Earth. The discovery of thousands of exoplanets in recent years creates an illusion of abundance, making it seem like habitable worlds should be common. However, this apparent plenty masks an extreme rarity, because simply having a planet orbiting a star is not nearly enough. The Fermi paradox, which famously asks where everybody is if the universe should be teeming with life, becomes more compelling when we realize that existence alone does not equate to habitability. Each requirement for life acts as a stringent filter, dramatically whittling down the number of viable candidates. For instance, a planet must reside in the so-called habitable zone where temperatures allow liquid water to exist, but that is just the starting point. The star itself must be stable over billions of years, not prone to violent flares that would sterilize nearby worlds. The planet needs a protective magnetic field to shield its atmosphere from being stripped away by stellar winds. An atmosphere that must have the precise composition to sustain life and regulate temperature. Geological activity, like plate tectonics, is crucial for recycling nutrients and maintaining climate stability over eons. The presence of a large moon might be necessary to stabilize the planet's axial tilt, preventing chaotic climate shifts. A planetary system might need a giant gas planet in the right position to act as a shield against frequent comet impacts, but not so close as to disrupt orbits. The planet's rotation speed affects its magnetic field and weather patterns, while its core must remain active to drive that magnetic dynamo. The atmosphere must balance greenhouse gases to avoid freezing or overheating, and it must block harmful radiation without stifling the light needed for energy. Water must be present and abundant, delivered perhaps by comets during the planet's early history, but not so much that it covers all land or so little that it leads to deserts. The planet's formation history matters, avoiding too many catastrophic collisions or too few to bring essential elements. The timeline for evolution is another huge hurdle. Life on Earth took billions of years to develop, from simple microbes to complex organisms, requiring an exceptionally stable environment throughout that period. Any major disruption, a supervolcano, an ice age, a radiation burst, could reset or halt that progress. The chemistry for life's origin is another bottleneck. Even with perfect conditions, the leap from non-living molecules to self-replicating life is a mysterious process that might be extraordinarily rare. When we add all these filters together, The number of planets that could host life plummets, the vastness of space, instead of assuring us of company, might actually emphasize our isolation. Each filter represents a chance for a planet to fail the habitability test, and with so many tests, the odds stack against life emerging easily. This is the core of the paradox. A universe filled with countless stars and planets might still be largely barren because the conditions for life are so specific and interconnected. The abundance we perceive is a trick of scale. While there are innumerable worlds, the fraction that are truly habitable could be vanishingly small. This realization should humble us. Earth might not be a typical world, but a cosmic fluke, a winner in a lottery with astronomical odds. The search for extraterrestrial life continues, driven by curiosity and hope. But we must acknowledge that every new discovery of a rocky planet in a habitable zone is just the first step in a long evaluation. Our methods for detecting life, such as looking for biosignatures in atmospheres, are still primitive and prone to false positives from non-biological processes. We might be limited by our own biases, searching for life as we know it based on carbon and water, while entirely different biochemistries could exist in environments we consider hostile. The sheer distances involved also mean that even if life is out there, we might never find it or communicate with it within a human lifetime. The universe offers a stage of immense proportions, but the play of life might have very few actors, or perhaps only one that we know of. This perspective does not diminish the wonder of exploration. It enhances the value of our own planet and the life it sustains. Understanding the rarity of habitable worlds could inspire greater efforts to protect Earth's delicate biosphere. As we develop better telescopes and space missions, we will learn more about these filters and perhaps find that some are more common than we think, or that life is more resilient and adaptable. But for now, the paradox stands. A full universe does not guarantee planets full of life, and the silence from the cosmos might be telling us that we are, for now, alone. This loneliness is not necessarily a sad truth, but a call to appreciate the unique conditions that allowed us to evolve and to continue searching with open minds. The journey to understand our place in the cosmos is just beginning, and each discovery brings new questions. The vastness that intimidates us also invites us to explore, to learn, and to cherish the fragile oasis we call home. So next time you look up at the stars, remember that each pinpoint of light could be a sun with planets, but the path to a living world is narrow and fraught with challenges, making every potential discovery a momentous event. The universe is big, but life might be small in comparison, and that makes our existence all the more precious. We are part of a grand experiment, and whether we are common or rare, the quest to know drives us forward. The filters of habitability are many, and each one narrows the field, but they also define what makes a world truly alive. From the right star to the right moon, from magnetic field to atmospheric balance, the checklist is long, and meeting every item is a monumental task for nature. The cosmos does not give away its secrets easily, and the search for another Earth is a testament to human curiosity and resilience. In the end, the paradox of vastness versus rarity reminds us that statistics alone cannot answer the deep questions about life. Only exploration and evidence can. So we keep looking, keep wondering, and keep reaching for the stars, aware that the answer might be just beyond our grasp, or that we might be the only ones asking the question. The universe is full of possibilities, but possibilities are not certainties, and that is what makes the search so compelling. Every new planet found is a data point, a piece of the puzzle, and while the puzzle is complex, the effort to solve it is worthy. The filters are real, and they shape the cosmic landscape of life, but they also highlight the incredible series of events that led to us. So as we ponder the night sky, We can marvel at both the immensity and the intimacy of our cosmic home, a tiny speck in a vast ocean, yet teeming with life against all odds. The paradox is not a barrier, but a motivation, pushing science to new heights and reminding us of the beauty and fragility of existence. The universe may be mostly empty, but that emptiness makes the pockets of life all the more significant. We are part of something vast and mysterious, and our journey to understand it is one of the greatest adventures of all time. So, after considering how many filters a planet must pass to be truly habitable, we often latch onto the most famous one, the idea of the habitable zone. This concept, sometimes called the Goldilocks zone, seems straightforward enough. It is that region around a star where it is not too hot and not too cold, where the temperature is just right for liquid water to potentially exist on a planet's surface. Water is essential for life as we know it, so this zone feels like a great place to start looking. But here is the catch. This idea, while useful as a basic screening tool, is dangerously simplistic. It paints with a very broad brush and makes several huge assumptions that often do not hold true in the messy reality of the cosmos. First and foremost, the classic habitable zone model assumes the star in question is a stable, well-behaved star, like our Sun. It assumes the planet has an atmosphere roughly similar to Earth's, with the right pressure and composition to maintain that liquid water. In reality, most stars are not like our Sun, and most planets will not have an Earth-like atmosphere. The definition is fundamentally passive. It only considers the amount of starlight the planet receives. It does not account for what the planet is actually like. A planet orbiting squarely within this zone could be a gas giant, like a mini Neptune, with no solid surface to speak of, rendering the idea of surface water moot. It could be a barren, airless rock, like Mercury, but further out, where any water would instantly boil away or freeze solid without an atmosphere to create pressure and trap heat. Imagine a rocky planet with no magnetic field. Even if it started with water, the solar wind from its star could strip away its atmosphere over time, leaving it a dry wasteland. Mars is a perfect example. It lies on the outer edge of our Sun's habitable zone, and it has water ice, but it lost its thick atmosphere and magnetic field, so liquid water cannot persist on its surface. The habitable zone concept also largely ignores the geology of the planet itself. A world without active plate tectonics might lack the carbon silicate cycle that acts as a planetary thermostat, regulating carbon dioxide levels and keeping temperatures stable over billions of years. A planet with extreme volcanic activity could choke its atmosphere in toxic gases or create a runaway greenhouse effect, turning a theoretically temperate world into a hellscape like Venus, which is also near the habitable zone's inner edge but is far too hot for life. The activity of the star itself is a critical factor the basic zone does not incorporate. Many of the most common stars in our galaxy are red dwarfs. These stars are smaller and cooler, which means their habitable zone is much closer in. However, red dwarfs are often prone to violent flares and eruptions of ultraviolet radiation. A planet orbiting close enough to be warm would be baked by these stellar outbursts, which could simultaneously scorch the surface and blow away the atmosphere. Furthermore, at such close orbits, the planet would likely be tidally locked, with one side in perpetual daylight and the other in eternal night, creating extreme temperature differences that could make global climate stability difficult. The simple liquid water possible rule also fails to consider the source of a planet's heat. We focus on stellar radiation, but there is another source: internal heat from radioactive decay and gravitational friction. This is where the concept gets turned on its head. Consider the moons of gas giants in our own solar system, like Jupiter's Europa or Saturn's Enceladus. These icy worlds are far outside the traditional habitable zone, where sunlight is weak, yet They are not frozen solid all the way through. The immense gravitational pull from their host planets flexes and heats their interiors, maintaining vast, global subsurface oceans of liquid water beneath the icy crusts. These are dark, underwater environments, but they could potentially harbour life, completely independent of sunlight. This means a world can be habitable without being in the habitable zone at all, challenging the very foundation of the definition. Another layer of complexity involves the atmosphere's composition and thickness. The habitable zone calculation typically uses an Earth-like atmosphere as a reference, but a planet with a much thicker atmosphere, rich in greenhouse gases like methane, could be warm enough for liquid water even far outside the standard zone. Conversely, a planet with a thin atmosphere might be frozen even well inside it. The presence of water itself is not guaranteed just by location. A planet might form dry, without enough water delivered by comets or asteroids. Or it might have too much water, becoming a water world with no continents, and perhaps no nutrient cycling needed for complex life. The planet's history is also vital. Was it bombarded by asteroids early on, seeding it with organic molecules and water? Or was the bombardment so intense it sterilized the surface repeatedly? Does it have a large moon to stabilize its axial tilt, preventing wild climate swings? The basic habitable zone tells us nothing about these factors. It is a one-dimensional view of a multi-dimensional problem. When scientists search for exoplanets, finding one in the habitable zone is exciting news, but it is merely the first and easiest hurdle. It is like finding a house that is the right distance from a power plant. It tells you the potential for electricity is there, but it says nothing about the condition of the house, whether it has wiring, plumbing, or is even safe to live in. The next steps involve characterizing the planet's atmosphere, looking for signs of gases like oxygen or methane that might indicate biological activity, and assessing its mass and density to see if it is rocky. But even with advanced telescopes, we can only glean so much information from light years away. The habitable zone is a useful starting point because it gives us a target list, a way to prioritize which planets to study more closely. However, relying on it alone would lead us to many dead ends. It creates a false sense of optimism, making us think we have found another Earth, when in fact we have only found a world that receives a similar amount of starlight. The true conditions for habitability are an intricate web of interconnected systems: the right star, the right planet size and composition, a protective magnetic field, an active geology, a stable climate system, and a dose of good fortune over billions of years. The Goldilocks zone is just the entrance gate to a much longer and more demanding obstacle course. As we discover more exoplanets, we are learning that nature is far more creative and varied than our simple models. We have found planets orbiting binary stars, planets with exotic compositions, and worlds in orbits we never thought possible. Each discovery forces us to refine our definitions and broaden our perspectives. The search for life requires us to look beyond this initial, simplistic filter and consider the full picture of what makes a world not just potentially habitable, but truly alive. It is a reminder that in science, our first ideas are often just approximations, and the real universe is always more complex and wonderful than we imagine. So, while the habitable zone will remain a key term in astronomy, its limitations are what truly teach us about the challenges of finding another home among the stars. We must be cautious not to oversimplify the cosmos, for it is in the details and the exceptions that the most interesting secrets are often hidden. The journey to find life is not just about locating a planet in the right spot. It is about understanding the deep and dynamic processes that allow life to arise and persist. This understanding helps us appreciate the incredible rarity and fragility of our own planet, a world that does not just sit in the right zone, but has all the other pieces of the puzzle perfectly in place. When we talk about a planet being in the habitable zone, we are implicitly making a huge assumption about the star it orbits. And that is where the story gets even more complicated. Most people naturally think of stars like our Sun when imagining other solar systems, but the reality is that our Sun is far from typical. In fact, the most common type of star in our Milky Way galaxy is the red dwarf, also known as an M-dwarf. These stars are much smaller, cooler, and dimmer than the Sun. Their abundance means that a large fraction of the planets we discover orbit these red dwarfs, which immediately forces us to reconsider what habitable really means. The habitable zone around a red dwarf is incredibly close to the star because the star emits so little heat and light. A planet would need to orbit very tightly, much closer than Mercury is to our Sun, to receive enough energy for liquid water to potentially exist. This proximity creates a host of problems that challenge the very possibility of life. One major issue is tidal locking, just like our moon is tidally locked to Earth, showing only one face. A planet orbiting so close to a red dwarf would likely become tidally locked to its star. This means one side of the planet would be in perpetual, blistering daylight, while the other side would be in eternal, freezing night. The temperature difference between these two hemispheres could be extreme, creating a world with a permanent day side that is scorching hot and a permanent night side that is frigidly cold. The Terminator line, the boundary between day and night, might be the only region with moderate temperatures. But even there, the conditions would be strange and likely unstable. Weather patterns would be bizarre, with constant winds howling from the hot side to the cold side, and the lack of a day-night cycle could profoundly affect any potential biochemistry or evolution of life. But the problems do not stop there. Red dwarfs are notoriously volatile. They are prone to frequent and powerful stellar flares, sudden eruptions that release immense amounts of energy, including ultraviolet and X-ray radiation. These flares can be hundreds or even thousands of times more powerful than anything our Sun produces. For a planet orbiting so close, these flares would bathe the surface in sterilizing radiation, repeatedly scouring it clean of any complex molecules that might be the building blocks of life. The planet's atmosphere would be under constant assault. A strong flare could potentially strip away the atmosphere over time, much like what likely happened to Mars, but on a much faster and more violent timescale. Even if a planet had a thick atmosphere or a strong magnetic field, the relentless bombardment from these flares would make it very difficult for life to gain a foothold or survive for long periods. The constant UV radiation would also break down complex organic molecules and make the surface uninhabitable without significant protection. Now, consider stars that are larger and hotter than our Sun, like O-type or B-type stars. These stars are incredibly luminous and burn through their fuel very quickly. Their lifetimes are short, only a few million to a few 100 million years, which is a mere blink in cosmic terms. For life to develop from simple single-celled organisms to complex multicellular beings, it requires billions of years of stable conditions. On Earth, it took nearly 4 billion years for intelligent life to emerge. A star that dies after only a few million years simply does not provide enough time for life to even begin, let alone evolve into something complex. The planetary systems around these massive stars are also often chaotic and violent, with intense radiation fields that would prevent the formation of stable environments. So, where does that leave stars like our Sun? G-type main sequence stars, like the Sun, appear to be in a sweet spot. They are stable for long periods, about 10 billion years, providing ample time for life to arise and evolve. They do not have the extreme flare activity of red dwarfs, and their habitable zones are at a comfortable distance, reducing the likelihood of tidal locking and allowing for a proper day-night cycle. This stability is crucial for the development of a complex biosphere. However, The catch is that sun-like stars are not the most common. They are outnumbered by red dwarfs by a huge margin. Estimates suggest that red dwarfs make up about 75% of all stars in the Milky Way. While sun-like stars might only account for a few percent, this means that when we are searching for habitable planets, if we focus only on sun-like stars, we are looking at a very small subset of the stellar population. The vast majority of potential real estate for planets is around these turbulent red dwarfs. This realization has forced astronomers to broaden their search and reconsider the conditions for habitability. Perhaps life could find a way on a tidally locked world, with life existing only in the twilight zone, or deep underground, or in the oceans shielded from radiation. Maybe some red dwarfs are calmer than others, with less flare activity, offering a glimmer of hope. But the fundamental challenge remains. The most common environment for planets in our galaxy is around stars that are inherently hostile to life as we know it. Our Sun, with its steady output and long lifespan, begins to look like a rare gem. Its stability allowed Earth to maintain liquid water and a relatively stable climate for billions of years, enabling the slow, gradual process of evolution to unfold. This longevity is not just about the star itself. It is about the entire system. A stable star means a stable energy source, which influences the planet's atmosphere, geology, and climate over astronomical timescales. The fact that our Sun is a relatively solitary star, not part of a multiple star system that could complicate planetary orbits, is another factor that might be more common than we think, but it still adds to the list of favourable conditions. When we combine the rarity of sun-like stars with all the other filters we have discussed, the need for a large moon, a magnetic field, plate tectonics, the right atmospheric composition, and so on, the probability of finding another Earth-like planet around a sun-like star seems to shrink even further. This does not mean that life is impossible around red dwarfs. It just means that the path to life there is much more fraught with peril. Our search strategies have to account for this. Missions like the James Webb Space Telescope are studying the atmospheres of planets around both red dwarfs and sun-like stars, trying to understand the effects of stellar activity on planetary environments. Every new discovery helps us refine our models. We are learning that some red dwarf planets might have thick atmospheres that distribute heat more evenly, mitigating the effects of tidal locking. Others might have strong magnetic fields that deflect stellar radiation. But these are additional requirements, more filters that a planet must pass. The prevalence of red dwarfs means that if life is common in the universe, it is most likely to be found on worlds that are very different from Earth, orbiting stars that are very different from the Sun. Alternatively, if life requires the long-term stability of a Sun-like star, then it might be exceedingly rare. This shifts our perspective on our own place in the cosmos. Our solar system, with its G-type star, might be a special place, not the standard model for galactic planetary systems. As we continue to explore the galaxy, we must keep our minds open to the possibility of life in extreme environments, but also acknowledge that the conditions that fostered our own existence might be far more exceptional than we ever imagined. The ideal stellar type for life might indeed be a star like our Sun, but if such stars are the exception and not the rule, then the cosmic abundance of stars does not automatically translate to an abundance of living worlds. It is another layer of complexity in the great puzzle of finding habitable planets, reminding us that every piece of the cosmic machine must align just right for life to flourish. The silence we hear from the universe might not be due to a lack of planets, but a lack of the right kinds of stars, with the right kinds of planets in the right kinds of orbits for long enough periods. So, the next time you look up at the Sun, remember that its steady, gentle warmth is a luxury that might be uncommon in the grand scheme of the galaxy, making our pale blue dot even more precious. But even with the right kind of star, a planet's journey towards habitability is far from guaranteed. and one of the most overlooked yet critical factors might be hanging in the sky above us. A large moon. Our moon seems so natural and permanent, but its role goes far beyond providing light at night or causing tides. It acts as a fundamental stabilizer for the entire planet's climate, and without it, Earth could be a wildly different and likely uninhabitable world. The key to this stability lies in the planet's axial tilt, that slight lean which gives us our seasons. Earth is tilted at about 23.5 degrees relative to its orbital plane, and this tilt is remarkably stable over vast stretches of time. This stability is not an accident. It is enforced by the gravitational pull of our relatively massive moon. The moon's gravity exerts a gentle but constant torque on Earth's bulge, damping down any potential wobbles and preventing the tilt from shifting erratically. Without this lunar anchor, Earth's axial tilt would be subject to chaotic variations, much like a spinning top that begins to wobble before it falls over. These variations could be extreme, with the tilt shifting by tens of degrees over periods of millions of years. Imagine a world where the tilt changes so much that the poles could effectively migrate towards the equator, turning entire climate zones upside down. Such dramatic shifts would cause catastrophic climate change, with ice ages forming in what were once tropical regions and deserts appearing where there was once ice. The stability provided by the moon has allowed Earth's climate to remain relatively predictable for billions of years, creating a long-term environment where life could not only emerge but also evolve and diversify into the complex forms we see today. This long-term stability is absolutely essential for the development of intelligent life, which requires eons of consistent conditions to develop. Now, consider Mars as a counterexample. Mars has two very small moons, Phobos and Deimos, which are essentially captured asteroids. They are too small to exert any significant gravitational influence on the red planet. As a result, Mars's axial tilt is known to vary chaotically over time, with shifts of up to 60 degrees possible. These extreme variations are thought to have contributed to the dramatic climate changes evident on Mars's surface, where evidence suggests water once flowed but now the planet is a frozen desert. If Earth had a similarly unstable tilt, the consequences would be dire. Agriculture as we know it would be impossible, as seasonal cycles would become unpredictable and extreme. Ecosystems would collapse under the strain of rapidly changing temperatures and weather patterns. The very rhythm of life, tied to stable seasons, would be shattered. So, how did Earth end up with such a large moon? The prevailing theory is the giant impact hypothesis, which suggests that early in the solar system's history, a Mars-sized body, often called Theia, collided with the proto-Earth. This violent impact was so immense that it vaporized part of both bodies and blasted a huge amount of material into orbit around Earth. This debris eventually coalesced to form our moon. This event was both catastrophic and fortuitous. It was a random act of cosmic violence that ultimately provided a key ingredient for long-term habitability. The moon we have is unusually large compared to its parent planet. The ratio of the moon's mass to Earth's is the largest in the solar system. This is not a common occurrence. For most rocky planets, such a massive impact early in their history is unlikely. Many may form without any moon, or with only small, captured asteroids that cannot provide the same stabilizing effect. This implies that a large dot, stabilizing moon might be a rare feature in the cosmos. When we look for exoplanets, we are essentially looking for worlds that have won a cosmic lottery, having undergone a specific, violent event that led to the formation of a substantial lunar companion. The moon's influence extends beyond just tilt stabilization. The tides it generates have played a role in the evolution of life, perhaps helping to mix nutrients in the oceans and creating intertidal zones that acted as nurseries for early organisms. However, the climate stabilization is its most crucial gift for complex life. It provides a steady platform upon which the slow, gradual process of evolution can build. Without it, the planet might be subject to a white Earth or slushball Earth scenario more frequently, where ice caps expand to the equator, or conversely, a runaway greenhouse effect where the entire planet becomes too hot. The moon helps to keep the climate system within bounds, preventing these extremes from becoming permanent states. This adds another stringent filter to the list of requirements for a habitable world. A planet needs to be in the right place, around the right star, with the right atmosphere and magnetic field. And now, it likely needs a large moon to keep its climate stable over astronomical timescales. When we combine this with all the other factors, the number of potential Earth-like planets shrinks even further. It is a humbling thought that our beautiful, life-filled world depends on a celestial accident that happened billions of years ago. As we search the heavens, we must consider that many potentially rocky planets in habitable zones might be rendered uninhabitable by a wildly shifting axis, doomed to climate chaos without a lunar guardian. This does not mean life is impossible on such worlds, but it makes the path to complex, intelligent life much more difficult, if not impossible. Life might cling on in simple forms, but the stability needed for technological civilizations to arise requires a consistency that only a large moon can provide over billions of years. So, the next time you see the moon, remember that it is not just a silent companion, it is an active participant in making Earth a home. A gravitational guide that has quietly steered our climate towards stability. Its presence is a testament to the intricate and interconnected systems that make a planet livable. In the grand search for other habitable worlds, we must now add "look for a big moon" to our checklist, knowing full well that such a feature might be one of the rarest of all. This understanding deepens the mystery of our own existence and highlights the fragility of the conditions that allow us to be here. The cosmic silence might not just be about a lack of signals, but a lack of stable, moon-anchored worlds where civilizations could last long enough to look up and wonder. But even with a large moon stabilizing the climate and a star providing steady energy, a planet faces another relentless threat from space, one that requires an invisible, global force field to survive, a magnetic field. This isn't science fiction. It's the real, powerful magnetosphere generated by Earth's churning, molten iron core. And it acts as our planet's primary defense against the constant stream of charged particles flowing from the sun, known as the solar wind. Without this protective bubble, our atmosphere would be slowly but surely stripped away, leaving the surface exposed to harsh radiation and transforming a vibrant world into a barren wasteland. Think of it as a planetary force field that deflects most of the dangerous solar and cosmic radiation, bending it away from the atmosphere and towards the poles, where it creates beautiful auroras but does no harm to life on the surface. The process that creates this field is called the dynamo effect, where the convection currents in the liquid outer core, combined with the planet's rotation, generate electrical currents that produce a global magnetic field. This is a dynamic ongoing process that requires a very specific internal structure. A planet must have a sufficiently large and hot metallic core that remains molten over billions of years, and it must be rotating at a speed that helps to stir this molten metal effectively. Not all rocky planets have this. A great example is our neighbour Mars. Mars is a stark warning of what happens when a planet loses its global magnetic field. Scientists believe Mars once had a much thicker atmosphere and flowing water on its surface, but its smaller size meant its interior cooled faster. Its core likely solidified or ceased its vigorous convective motion, shutting down the planet-wide magnetic dynamo. Without this shield, the solar wind, a supersonic flow of protons and electrons, has been directly impacting the Martian upper atmosphere for eons. knocking atoms loose and blasting them off into space. This process, called sputtering, has stripped away the majority of Mars's atmosphere, leaving it with a surface pressure less than 1% of Earth's. The loss of atmosphere led to the evaporation and escape of its surface water, turning a potentially habitable world into the cold, dry desert we see today. The same solar wind that gives us gentle auroras was, for Mars, a destructive force that fundamentally changed its destiny. Now, imagine if Earth lacked its magnetic field. The solar wind would gradually erode our nitrogen and oxygen atmosphere, molecule by molecule. Over millions of years, our air would become thinner and thinner. The immediate consequences would be dire. Without the atmospheric pressure, liquid water could not exist on the surface. It would either boil away or freeze. The increased surface radiation from both the sun and galactic cosmic rays would be devastating for life. This radiation bombards the surface, damaging DNA and preventing the development of complex multicellular organisms. On Earth, life was able to venture onto land and evolve into more complex forms, in part because the magnetosphere and atmosphere together provided a relatively safe environment, filtering out the most harmful rays. Microbes might survive underground or in deep oceans, but the rich, diverse ecosystems we see on Earth's surface would be impossible. The magnetic field also protects our technological infrastructure. Solar storms, which are intense bursts of solar wind, can induce powerful electrical currents in long conductors like power lines and pipelines, potentially causing widespread blackouts and damaging satellites. Our magnetosphere acts as a buffer, absorbing and redirecting much of this energy. The requirement for a strong, lasting magnetic field adds another rigorous filter to the list of conditions for a habitable world. A planet must be large enough to retain internal heat for billions of years, powering the convection in the core. It likely needs a composition that includes significant amounts of radioactive elements like potassium, thorium, and uranium, whose decay provides a long-lasting heat source to keep the core molten. The planet's rotation is also a factor. A very slow rotation, like that of Venus, might not generate a strong enough dynamo effect. Even if the core is partially liquid, Venus rotates so slowly that its day is longer than its year, and it has no global magnetic field, though it may have a very weak one induced by the solar wind interacting with its upper atmosphere. Its thick atmosphere has survived due to other factors, but it shows that rotation speed matters. Furthermore, the history of the planet's formation is crucial. A giant impact, like the one that formed our moon, might have reset or altered the core's structure, potentially delaying or preventing the onset of a dynamo. The magnetic field is not a static thing. It can weaken, strengthen, and even reverse its poles over time, as it has on Earth. But the key is that it must persist for geologic eras to provide the stable protection necessary for life to flourish and evolve. When we look for exoplanets, we cannot directly observe their magnetic fields from light years away. We infer their potential based on their size, density, dot, and estimated composition. A planet with a density suggesting a large iron core is a good candidate, but we cannot know for sure if that core is still molten and convecting. This adds a layer of uncertainty to our assessment of a planet's habitability. We might find a world that is the right size, in the habitable zone, around a stable star, and even with a possible large moon. But if it lacks an active magnetic dynamo, it could be a dead world slowly losing its life support system. The magnetic field is thus a silent, invisible guardian, one we often take for granted. It works tirelessly in the background, allowing our atmosphere to remain thick and protective, enabling liquid water to flow, and shielding the delicate chemistry of life from the harsh realities of space. Its necessity makes the search for another Earth even more challenging. Every time we narrow down the candidates with another filter, the number of potential worlds shrinks. The magnetic field is a non-negotiable part of the planetary package for sustaining a complex biosphere over billions of years. It is not enough to have the ingredients for life. You must also have the durable packaging to keep those ingredients safe from the cosmic elements. As we continue to explore our own solar system and beyond, understanding magnetic fields will be key to interpreting the histories and futures of other worlds. The presence of a strong magnetosphere might be one of the ultimate markers of a world that can not only birth life, but also nurture it long enough for that life to gaze up at the stars and wonder about its own origins. So, the next time you see a compass needle point north, remember that it is responding to a deep dot, planetary power that is, in its own way, just as vital for life as the sun or water. It is a humbling reminder of the intricate and fragile interplay of forces that make our world a home, and it underscores the possibility that such a perfect combination of shields and stabilizers might be exceptionally rare in the cosmos. So, we have this protective magnetic field shielding us from above. But what about the engine room deep within the planet? That is where another critical process unfolds, one that is just as vital for long-term habitability: the dynamic geology of plate tectonics. This is not merely about causing earthquakes or building mountains. It is a planet-wide recycling and regulation system that acts as a thermostat for the global climate and a mixer for essential chemicals, without which Earth could easily become either a frozen ball or a scorching greenhouse. The Earth's crust is broken into several large plates that float on the hot, semi-fluid mantle below. These plates are in constant, slow motion, drifting apart in some places, colliding in others, and sliding past one another. This movement drives the creation of new crust at mid-ocean ridges and the destruction of old crust at subduction zones, where one plate dives beneath another back into the mantle. This continuous cycle is the heart of the planetary regulation system. One of its most crucial functions is managing the carbon dioxide levels in the atmosphere through the carbon silicate cycle. When atmospheric CO2 levels rise, perhaps from volcanic activity, the planet warms due to the enhanced greenhouse effect. This warmer temperature increases rainfall, which accelerates the weathering of silicate rocks on the continents. Rainwater, slightly acidic from dissolved CO2, reacts with these rocks, breaking them down and washing the resulting minerals, including calcium and bicarbonate ions, into the oceans. In the oceans, marine organisms use these ions to build their shells and skeletons from calcium carbonate. When these organisms die, their shells sink to the ocean floor, eventually becoming part of the sedimentary layer. Now, here is where the tectonics come in. Through subduction, that seafloor sediment, rich in carbon, is pulled down into the mantle. The heat and pressure eventually cause the carbonate rocks to break down, releasing CO2 that makes its way back to the surface through volcanic eruptions. This entire process acts as a giant, slow-motion thermostat. If the planet cools too much, for instance during an ice age, chemical weathering slows down, less CO2 is removed from the atmosphere, and volcanic outgassing continues to add CO2, gradually warming the planet back up. Conversely, if it gets too warm, weathering accelerates, drawing down more CO2 and cooling the planet over millions of years. This negative feedback loop has maintained Earth's temperature within a range that allows for liquid water for billions of years, despite the sun's increasing brightness over time. Without this geological thermostat, a planet's climate would be far more unstable, prone to runaway cooling or heating. Venus, for example, shows no evidence of active plate tectonics. While it may have had water in the past, the lack of a mechanism to recycle carbon dioxide likely contributed to a runaway greenhouse effect. leaving it with a crushing atmosphere of CO2 and surface temperatures hot enough to melt lead. Mars, too, is a geologically stagnant world, with no plate tectonics to regulate its climate or recycle nutrients, and it lost its atmosphere and water. Beyond climate control, plate tectonics is also a master recycler of nutrients essential for life. The process constantly brings fresh, mineral-rich material from the mantle to the surface through volcanism and mid-ocean ridge activity. It also pushes surface rocks containing vital elements like phosphorus, potassium, DOT, and sulfur back into the mantle, only to be re-released later. This geochemical cycling enriches the crust and the oceans, providing the raw materials that life needs to thrive. It creates diverse environments and habitats, from deep ocean trenches to high mountain ranges, driving biodiversity. The continents themselves are a product of tectonics. Without them, Earth might be a water world with no land masses, potentially limiting the evolution of complex life. The energy and heat from the planet's interior that drive this process are also crucial. A world must be sufficiently large and have enough internal heat from its initial formation and from the decay of radioactive elements to maintain a convecting mantle and a liquid outer core, which powers both the magnetic field and the tectonic engine. This requirement for internal heat adds another filter to planetary habitability. A planet that is too small, like Mars, cools quickly and its geological activity grinds to a halt. But even a planet of the right size might not develop plate tectonics if its crust is too thick or its mantle too stiff. The specific conditions that allow for the fragmentation of the lithosphere into mobile plates might be uncommon. Some scientists propose that the presence of water acts as a lubricant for subduction, making it easier for plates to slide and sink. If that is the case, a planet needs water not just on its surface but also incorporated into its rocks to initiate and sustain tectonics. This introduces a chicken and egg problem. You need water for tectonics, but tectonics helps regulate the climate to keep water liquid. The initiation of plate tectonics on Earth is still a topic of debate, and it might have been triggered by a massive asteroid impact or internal processes that are not guaranteed on other worlds. Furthermore, the style of tectonics matters. Earth has a particular mode called mobile lid tectonics, where the plates move independently. Other planets might have stagnant lid tectonics, like Mars and Venus, where the crust forms a single, unbroken shell, and heat escapes primarily through volcanic hotspots without widespread crustal recycling. In a stagnant lid regime, the planet can still have volcanism, but it lacks the continuous, large-scale recycling that regulates climate and nutrients so effectively on Earth. The planet might experience episodic, catastrophic resurfacing events, but these would not provide the steady, fine-tuned control needed for long-term climate stability. The benefits of plate tectonics extend over astronomical timescales. It provides the stability that allows life the time to evolve from simple single-celled organisms to complex multicellular life. It helps maintain the redox state of the planet, influencing the chemistry of the oceans and the atmosphere. It even plays a role in generating the magnetic field, as the heat loss from the core driven by mantle convection is part of what powers the dynamo. When we search for habitable exoplanets, we look for rocky worlds in the habitable zone, but we have no direct way to detect plate tectonics from light years away. We can infer a planet's potential for tectonic activity based on its size, density, and estimated internal heat, but we cannot be certain. A planet that seems perfect in every other way might be geologically dead, lacking this essential climate-stabilizing mechanism. This means that many exoplanets we classify as potentially habitable might be stagnant worlds, unable to regulate their temperature over billions of years and thus unable to support complex life. The combination of a magnetic field and active plate tectonics creates a powerful synergy for protecting and sustaining a biosphere. The magnetic field guards the atmosphere from erosion, while plate tectonics manages the composition of that atmosphere and the chemistry of the oceans. Together, they create a resilient, self-regulating system. The rarity of this combination further constrains the number of worlds that could truly be Earth-like. It is not enough to have the right distance from a star. A planet must also have a dynamic, living interior. Our Earth is not just a rock with water. It is a geologically active world, a complex machine with moving parts that maintain its habitability. This internal engine is as crucial as any external factor, and its potential scarcity in the universe makes our own planet all the more special. As we continue to explore understanding the geology of exoplanets will be a major challenge, but it is essential for answering the question of whether we are alone. The silent, slow dance of the tectonic plates beneath our feet is a dance of life, a fundamental rhythm that has shaped our world's history and destiny. Without it, the story of life on Earth would have been very different, and the chances of finding a similar story elsewhere become that much slimmer. Now, while plate tectonics works deep below to regulate our planet's climate and chemistry through the slow recycling of carbon and minerals, the atmosphere itself is the immediate environment where life exists, and its precise chemical makeup is a delicate balancing act that goes far beyond the presence of oxygen alone. When we point our telescopes at distant exoplanets, one of the primary signs we hunt for is molecular oxygen in their atmospheres. And this focus is well founded. Oxygen is a highly reactive gas. It readily engages in chemical reactions with other elements, such as iron in rocks or carbon in organic compounds, meaning that it doesn't persist for long in a free state without a continuous source replenishing it. On Earth, the abundant oxygen that makes up about 21% of our atmosphere is almost entirely a product of biological activity, specifically from photosynthetic life forms like plants, algae, and cyanobacteria. These organisms use sunlight, water, and carbon dioxide to produce energy and release oxygen as a waste product. If all photosynthesis were to cease, though, the oxygen in our air would gradually be consumed by reactions with surface materials and other gases, diminishing over a few million years, which is a blink in geological time. Therefore, detecting oxygen in the atmosphere of another world is thrilling because it hints at ongoing processes that could be biological. But it is crucial to understand that oxygen by itself is not a definitive marker of habitability or even life. An atmosphere rich in oxygen but lacking other components could be unstable or even hostile. For instance, it would promote rampant combustion and might not provide the necessary greenhouse warming or protection from radiation. The true measure of a habitable atmosphere is its overall chemical equilibrium, a sophisticated blend of gases that collaboratively maintains a stable surface temperature, shields the planet from harmful stellar radiation, and facilitates the chemical processes that life requires. This equilibrium depends critically on the presence and proportions of greenhouse gases. The greenhouse effect is a natural process where certain gases in the atmosphere trap infrared radiation emitted by the planet's surface, preventing it from escaping into space and thus warming the planet. Without any greenhouse effect, Earth's average surface temperature would be around 0 degrees Fahrenheit, far below the freezing point of water, making life as we know it impossible. The primary greenhouse gases include carbon dioxide, water vapour, methane, DOT, and nitrous oxide, each with different potencies and lifetimes in the atmosphere. However, the key is their concentration. It's a Goldilocks scenario where too little or too much can be disastrous. Consider Mars. It has an atmosphere composed mostly of carbon dioxide, but it is extremely thin, with a surface pressure less than 1% of Earth's. This thinness means that even though CO2 is a greenhouse gas, the overall effect is minimal, and Mars is bitterly cold, with average temperatures around -80 degrees Fahrenheit. preventing liquid water from existing stably. In contrast, Venus presents the opposite extreme. Its atmosphere is immensely thick and composed of over 96% carbon dioxide, creating a powerful greenhouse effect that traps solar energy efficiently. This results in surface temperatures soaring to around 860 degrees Fahrenheit, hot enough to melt lead and zinc. The difference between these two neighbours underscores the necessity for a balanced greenhouse effect. For a planet to be habitable, it must have just the right amount of greenhouse gases to maintain temperatures within a range that allows liquid water to persist, typically between 32 and 212 degrees Fahrenheit. This balance is dynamic and influenced by various factors, including volcanic outgassing that adds carbon dioxide, biological processes that can consume or produce gases, and geological cycles like weathering that remove CO2 from the atmosphere. Water vapour is another crucial component and a potent greenhouse gas. Its concentration in the atmosphere is highly dependent on temperature. Warm air can hold more water vapour, which in turn traps more heat, creating a positive feedback loop that can amplify warming. On Earth, this potential runaway effect is kept in check by negative feedbacks, such as increased cloud cover that reflects sunlight back into space, and by the planetary climate system that includes ocean currents and atmospheric circulation. Moreover, the interaction between the atmosphere and the Earth's geology, particularly through plate tectonics, plays a vital role in regulating long-term climate. For example, the weathering of silicate rocks on continents absorbs carbon dioxide from the atmosphere, forming carbonate minerals that are eventually transported to the oceans and subducted into the mantle, sequestering carbon for millions of years. Volcanic activity then releases CO2 back into the atmosphere, completing the cycle. This carbon silicate cycle acts as a planetary thermostat, helping to stabilise Earth's climate over geological timescales. However, for such a system to function, the atmosphere must have the appropriate composition to allow these chemical interactions to occur efficiently. If the atmosphere is too rich in inert gases or lacks the necessary reactants, this regulatory mechanism might not operate, leading to climate instability. Beyond temperature control, the atmosphere serves as a protective shield against harmful radiation from space. Solar radiation includes ultraviolet light, which has enough energy to break chemical bonds in DNA and other biological molecules, causing mutations and cell damage. Earth's atmosphere contains a layer of ozone, a molecule composed of 3 oxygen atoms, which absorbs most of the incoming UV radiation. This ozone layer is itself a product of atmospheric chemistry driven by sunlight and the oxygen produced by life. Without biological activity to maintain oxygen levels, the ozone layer would dissipate, exposing the surface to dangerous UV levels. But protection must be balanced with transparency. The atmosphere must allow visible light to pass through to the surface, because this light is essential for photosynthesis, the process by which plants and other organisms convert solar energy into chemical energy. On Earth, our atmosphere is largely transparent to visible light, while blocking most UV, striking a perfect balance that supports a thriving biosphere. If the atmosphere were too thick or hazy, it could block too much visible light, stifling photosynthesis, or if too thin, it would offer insufficient protection. Atmospheric pressure is another critical factor influenced by composition. Pressure affects the physical state of water. At low pressures, water boils at lower temperatures, making it difficult for liquid water to exist. Mars, with its low atmospheric pressure, cannot sustain liquid water on its surface. Any water would either freeze or sublimate. On the other hand, Venus has an extremely high atmospheric pressure, about 90 times that of Earth, which contributes to its intense greenhouse effect and makes the surface inhospitable. The ideal atmospheric pressure for habitability allows liquid water to exist across a range of temperatures and supports the biochemical processes of life. Achieving this requires a planet with sufficient mass to gravitationally hold an atmosphere, but not so much that it accumulates a thick envelope of light gases like hydrogen and helium. Additionally, a magnetic field is necessary to deflect the solar wind, preventing the atmosphere from being eroded over time, as happened on Mars. The specific mix of gases also includes inert components that play supporting roles. Nitrogen, which makes up about 78% of Earth's atmosphere, is largely non-reactive and serves as a diluent, preventing oxygen from causing widespread fires and providing a stable background for chemical reactions. Nitrogen is also a key element in amino acids and nucleic acids, fundamental to life. Other gases, such as argon, are present in trace amounts and are chemically inert, but their presence can influence atmospheric density and behaviour. When searching for biosignatures, scientists look for gases that are in chemical disequilibrium, meaning they shouldn't coexist without a continuous source. For example, the simultaneous presence of oxygen and methane is a strong indicator of life because these gases react with each other to form carbon dioxide and water, so their persistence suggests ongoing production. However, abiotic processes like volcanic activity or photochemistry can also produce some of these gases, leading to false positives. Therefore, interpreting atmospheric data requires a comprehensive understanding of the planetary context, including its star, geology, and history. In conclusion, the correct atmospheric composition for a habitable planet is a complex and finely tuned system involving more than just oxygen. It requires a balanced combination of greenhouse gases to regulate temperature, protective layers to shield against radiation, and a mix of reactive and inert gases that support life's chemistry. This balance is influenced by the planet's size, distance from its star, geological activity, magnetic field, and biological processes. The fact that Earth has maintained such a stable and supportive atmosphere for billions of years is a remarkable outcome of numerous factors working in concert. As we explore the cosmos, we recognize that finding another world with a similarly perfect atmospheric recipe is a daunting challenge, making each candidate a precious object of study. The atmosphere is indeed the bubble of life, and achieving its delicate harmony might be one of the universe's greatest rarities. So we have talked about the planet itself, its atmosphere, and its internal processes, but a world does not exist in isolation. It is part of a broader solar system, and the other planets in that system, particularly any gas giants, can play a massive role in determining its fate. This brings us to what is often called the Jupiter effect, the idea that a giant planet can act as both a protective guardian and a destructive threat, and the difference hinges on a very delicate balance. In our own solar system, Jupiter, with its immense gravitational pull, is thought to have acted like a cosmic vacuum cleaner or a gravitational shield for the inner planets. During the early, chaotic days of the solar system, the region beyond Mars was filled with countless leftover planetesimals, comets, and asteroids. Jupiter's powerful gravity perturbed the orbits of many of these objects, flinging some of them out of the solar system entirely and capturing or consuming others. This process is believed to have significantly reduced the number of catastrophic impacts on Earth, potentially creating a more stable environment where life could take hold and evolve without being constantly reset by world-altering collisions. The frequency of such extinction-level events was likely lower thanks to Jupiter's presence, giving evolution the extended periods of stability it needed to produce complex life. This is the benevolent view of Jupiter, the protective big brother watching over the inner solar system. However, this same gravitational influence can be a double-edged sword. A gas giant's gravity is not selectively benevolent. It is a fundamental force that shapes the entire architecture of the planetary system. If a Jupiter-like planet were to form in the wrong place, or if its orbit were unstable, it could have devastating consequences for any terrestrial planets in the system. For instance, a giant planet migrating inward from where it formed could ruthlessly eject smaller, rocky planets from the system altogether, sending them spiraling into the cold darkness of interstellar space. Even without full-scale ejection, a giant planet's gravity can perturb the orbits of inner worlds, making them more eccentric or inclined. A planet with a highly elliptical orbit would swing wildly between extreme temperatures, moving very close to its star and then very far away, making stable climate conditions and liquid water virtually impossible. This kind of gravitational bullying could prevent a planet from ever achieving the long-term stability required for life. The mass of the giant planet is also a critical factor. A planet significantly more massive than Jupiter would exert an even stronger gravitational pull, potentially destabilizing a wider region of the planetary system and making it harder for Earth-like planets to form or remain in stable, circular orbits within the habitable zone. Conversely, a gas giant that is too small might not be effective at clearing out debris, leaving the inner system subjected to a much heavier and more frequent bombardment of comets and asteroids. This bombardment could be a dual-edged sword itself, while too many large impacts would be sterilizing. A moderate amount early on might have been crucial for delivering water and organic molecules to Earth. The timing and intensity of this late heavy bombardment are another variable that must be just right. Therefore, the position of the giant planet is perhaps the most crucial element. In our solar system, Jupiter orbits at a respectful distance from the Sun, beyond the asteroid belt. This location allows it to influence the inner system without dominating it destructively. Its gravity helps to shepherd the asteroid belt, preventing most of its members from coalescing into a planet, but also preventing them from easily migrating inward. If Jupiter were located much closer to the Sun, say in an orbit similar to Venus or Earth, its gravitational influence would have likely prevented the formation of the inner rocky planets altogether, or it would have disrupted their orbits beyond recognition. Our solar system would look completely different, probably devoid of any planets in the habitable zone. This scenario of hot Jupiters is actually quite common in other planetary systems we have discovered, where giant planets orbit extremely close to their stars. In such systems, the chances for a stable, habitable, Earth-like planet are dramatically reduced. The orbital dynamics become a complex dance, and the presence of a giant planet adds a powerful and unpredictable partner. Its gravitational tugs can resonate with other planets, either stabilizing or destabilizing their orbits over long timescales. Some theoretical models even suggest that a giant planet's gravity could help deliver water-rich comets from the outer system to the inner, drier planets, essentially seeding them with the ingredients for life. But again, this requires a precise setup. The giant planet must be in the right place to nudge comets inward without sending them on a direct collision course every time, or without ejecting the water-bearing material entirely. It is a gravitational balancing act of incredible delicacy. When we search for exoplanetary systems, we are now looking for architectures that might mirror our own in this specific regard. A gas giant residing in the outer system, leaving the inner region clear for potentially rocky worlds to form in stable, circular orbits within the habitable zone. We do not yet have the technology to detect every small, Earth-sized planet in every system, but we can study the orbits and masses of the giant planets. We do find a system with a hot Jupiter or with a giant planet on a highly eccentric orbit is considered a less likely candidate for hosting habitable worlds. The Jupiter effect forces us to expand our definition of habitability beyond a single planet. It is not enough for a world to have the right size. the right star and the right atmosphere, it must also have the right neighbours in the right orbits. A protective giant planet might be a crucial component for a biosphere that lasts long enough to develop complexity. This adds another formidable filter to the already long list of requirements for a habitable planet. It suggests that solar systems with a configuration like ours, which seems so natural and orderly, might be a rare outcome of planetary formation. The chaotic processes that govern the birth of planets often lead to systems that are very different from our own. The silent, watchful presence of a Jupiter in the outer system, a guardian that cleans up the cosmic neighbourhood without causing trouble, might be one of the key pieces that allowed life on Earth to flourish. So, when we gaze at Jupiter in the night sky, we can see it as a symbol of both cosmic protection and potential peril, a reminder that our existence depends on a fragile balance of forces that extend far beyond our own world. The search for life is therefore not just about finding another Earth. It is about finding another solar system with a similar architectural blueprint, where the giant planets have settled into orbits that nurture life rather than destroy it. This understanding makes our own cosmic address seem even more special, and the possibility of finding another like it even more remote. While the gravitational influence of a giant planet can help create a safer neighbourhood by reducing impact events, this is just one piece of a much larger puzzle. The absolute necessity of billions of years of uninterrupted stability for life to evolve from simple microbes to complex, intelligent beings. Think about the history of life on Earth. It took approximately 4 billion years for single-celled organisms to give rise to the vast diversity of plants, animals, and eventually, a species capable of looking back and questioning its own origins. This wasn't a quick process. It was a slow, gradual, and incredibly fragile journey that required the planet's environment to remain within a very narrow range of conditions for an almost incomprehensibly long time. Any major deviation, a runaway greenhouse effect turning the planet into a Venus-like oven, a global glaciation freezing it solid, a relentless bombardment of radiation from a hostile star, or the loss of a protective magnetic field, could have easily reset the clock or ended the story entirely. This need for long-term stability introduces one of the most daunting filters in the search for habitable worlds. The planetary system must be exceptionally quiet and the planet itself remarkably resilient over geological timescales. The star at the centre of it all plays the most critical role in this timeline. It must be stable, not for millions, but for billions of years. Our Sun is a G-type main sequence star, and it has provided a consistent, relatively gentle output of energy for over 4 billion years, with several billion more to go. This longevity is not a given. Many stars, like the volatile red dwarfs, are prone to frequent and violent flares that could sterilize nearby planets repeatedly, preventing life from ever gaining a foothold. On the other end, massive hot O-type or B-type stars burn through their fuel in only a few million years, dying in spectacular supernovae long before life could even begin to experiment with complexity. So, the star must have a lifespan measured in billions of years, not millions, and it must maintain a steady luminosity without dramatic fluctuations. But a stable star is only the first requirement. The planet itself must be a bastion of consistency. It needs to maintain a strong magnetic field for billions of years to protect its atmosphere from being stripped away by stellar winds. This requires a large, molten metallic core that remains active through radioactive decay and residual heat from formation, generating a dynamo effect. If the core cools and solidifies too quickly, as likely happened on Mars, the magnetic field vanishes and the atmosphere is slowly eroded into space, taking with it any chance for liquid water and a stable climate. The planet's atmosphere must also remain in a delicate balance. It needs the right mix of greenhouse gases to trap enough heat to prevent global freezing, but not so much that it triggers a runaway greenhouse effect. This balance is maintained through feedback loops like the carbon-silicate cycle, which itself depends on geological activity like plate tectonics. Plate tectonics recycles carbon dioxide between the atmosphere, oceans, and mantle, acting as a planetary thermostat over millions of years. Without this slow, regulatory process, a planet's climate could veer into extreme heat or cold, making it uninhabitable. The planet's water inventory must also be stable. It cannot lose all its water to space or have it entirely locked away in permanent ice. The initial delivery of water by comets and asteroids must be followed by a period where the planet can retain that water in liquid form on its surface. Furthermore, the planetary system as a whole must be relatively tranquil. While occasional asteroid impacts can deliver important organic molecules, a period of intense bombardment, like the late heavy bombardment in our solar system, must not be so severe that it sterilizes the planet repeatedly. After that, the system should settle down, with orbits stabilizing and catastrophic collisions becoming rare events. A giant planet like Jupiter can help by gravitationally clearing out debris, but as discussed, its position and mass must be just right to avoid causing gravitational chaos itself. The planet's orbit around its star should be fairly circular to avoid extreme seasonal temperature swings. A highly elliptical orbit would bring the planet too close to the star, boiling its oceans, and then swing it too far away, freezing them solid. The planet's axial tilt should also be stable. Earth's tilt is stabilized by its large moon, preventing chaotic wobbles that would cause dramatic climate shifts over millions of years. Without such a moon, a planet's tilt could vary wildly, turning polar regions tropical and vice versa, making any long-term climate stability impossible. Even with all these physical factors in place, the biological processes themselves require time. The transition from simple prokaryotic cells to more complex eukaryotic cells took over 2 billion years on Earth. The emergence of multicellular life required another significant leap. And the development of intelligence and technology took even longer. Each of these steps represents a bottleneck where evolution could have stalled indefinitely. For example, the Great Oxidation Event, when photosynthetic organisms began pumping oxygen into the atmosphere, was a catastrophic event for most life at the time, which was anaerobic. It took hundreds of millions of years for ecosystems to adapt, and for new, oxygen-breathing life forms to emerge. If such a transition had been interrupted by a global glaciation or a massive impact, complex life might never have arisen. The sheer length of time required means that the planet must avoid any number of potential show-stopping catastrophes. A nearby gamma-ray burst, a supernova explosion within a few dozen light-years, or a period of extreme volcanic activity could all deliver lethal doses of radiation or alter the atmosphere beyond recognition. The galaxy must be a relatively safe neighbourhood, without too many violent events in the vicinity. When we look at other planetary systems, we have to ask not just if a planet is in the habitable zone now, but whether it has been there, stable and undisturbed, for billions of years. This is incredibly difficult to determine from light years away. We can estimate the age of a star and its system, but we cannot easily know if a planet has maintained a thick atmosphere, a strong magnetic field, and liquid water for the requisite eons. The discovery of an Earth-sized planet in the habitable zone of an old star is exciting, but it doesn't guarantee that the planet has enjoyed continuous habitability. It might have undergone dramatic climate shifts, lost its water, or suffered atmospheric collapse in its past. The timeline of evolution thus imposes a filter that is both temporal and probabilistic. Among the countless planets in the galaxy, only a tiny fraction will have the combination of a long-lived stable star, a geologically active and well-shielded planet, and a quiet stellar neighbourhood that together provide a multi-billion-year window of opportunity. This makes the emergence of complex, intelligent life a potential cosmic rarity. It suggests that many worlds might host simple, microbial life for vast periods, but never make the leap to complexity simply because they cannot maintain the necessary stability for long enough. Our own existence is a testament to an unbroken chain of stability spanning 4 billion years, a chain that could have been broken at any point by countless natural disasters. This perspective humbles our search and deepens the value of our own planet. As we scan the heavens, we are not just looking for a planet that can support life today. We are looking for a planet that has supported life for ages and will continue to do so, a world with the endurance to nurture evolution's slow, beautiful, and uncertain journey. The silence we hear from the cosmos might not be a lack of life, but a lack of life that has had the time and stability to become complex and technological. The need for billions of years of stability is perhaps the most profound and challenging filter of all, reminding us that in the universe, patience is not just a virtue, it is a prerequisite for life itself. So, after considering the immense timescale required for evolution to unfold, we arrive at perhaps the most profound and least understood step of all, the actual origin of life from non-living matter. This is the field of prebiotic chemistry, the study of how simple inorganic molecules could have assembled into the first living organisms, and it represents a gigantic leap in complexity that we have only seen happen once, right here on Earth. Imagine a planet that has everything we've discussed so far: the right star, a stable climate for billions of years, a protective magnetic field, plate tectonics, and a perfect atmosphere. It has all the ingredients, like water, carbon, nitrogen, and various minerals, just sitting there. But then, the question is, how do those ingredients spontaneously organize themselves into something that is alive? How does chemistry become biology? This is not a simple step. It is the transition from a world of predictable chemical reactions to a world of self-replicating, evolving systems. And it remains one of the biggest unsolved mysteries in science. We know it happened on Earth because we are here, but the precise mechanisms are still largely speculative. The first step likely involved the formation of organic molecules, the building blocks of life. Experiments like the famous Miller-Urey experiment in the 1950s showed that by simulating the conditions of early Earth with a mixture of gases like methane, ammonia, hydrogen, and water vapour, and an energy source like electrical sparks to simulate lightning, amino acids, the components of proteins, could form spontaneously. This demonstrated that the basic ingredients for life could arise from non-living processes. However, going from a soup of amino acids and other molecules to a functioning cell is a leap of astronomical proportions. These molecules needed to assemble into more complex structures, like proteins and nucleic acids, and they needed to be contained within a membrane. Most importantly, a system needed to emerge that could copy itself, storing and transmitting information. This is the realm of RNA world hypotheses, which suggest that RNA, a molecule that can both store genetic information and catalyze chemical reactions, might have been the first self-replicating system, but forming long chains of RNA under prebiotic conditions is notoriously difficult. They are fragile and require very specific conditions to polymerize. So, where on early Earth could such delicate processes have taken place? Scientists have proposed several candidate environments that might have provided the right conditions. One leading idea is deep-sea hydrothermal vents. These are cracks in the ocean floor where superheated, mineral-rich water spews out into the cold, dark depths. They offer a constant source of energy and a rich chemical soup, with microscopic pores in the rock that could have acted as primitive cells, concentrating molecules and facilitating reactions. The temperature gradients and mineral surfaces could have helped catalyze the formation of complex organic molecules and provided protection from the harsh surface environment, which was likely bombarded by ultraviolet radiation from the sun. Another potential cradle is shallow tidal pools or lagoons. Here, wet-dry cycles could have been crucial. As pools evaporated, they would have concentrated organic molecules, encouraging them to link up into longer chains. Then, when water returned, these chains could interact and form more complex assemblies. Clay surfaces have also been suggested as possible catalysts. Their layered structures can attract and organize organic molecules, potentially leading to the formation of early genetic material or cell-like structures. Despite these plausible scenarios, the probability of life actually emerging in any given suitable environment is completely unknown. It might be that given the right conditions and enough time, life is almost inevitable. Or it could be that the specific sequence of chemical events required is so improbable that it represents a cosmic fluke, a fortunate accident that happened only once in our solar system. This is the concept of abiogenesis being a severe bottleneck. A planet could be perfectly habitable for billions of years, with all the necessary raw materials, and yet life might never spark into existence. The transition from non-life to life might require a very specific and rare combination of chemical concentrations, energy sources, and physical confinement that is not guaranteed even on a world that seems ideal. Furthermore, the time window for this to happen might be critical. On Earth, evidence suggests life appeared surprisingly quickly after the planet cooled and liquid water became available within a few 100 million years. This rapid emergence might imply that the process is relatively easy once conditions are right. However, it could also mean that we are just lucky, and that on other worlds, the process could take much longer or never occur at all. The fact that we have only one data point, life on Earth, makes it impossible to draw firm statistical conclusions. We do not know if life is a common outcome of planetary evolution or a rare exception. This uncertainty directly impacts our search for life beyond Earth. When we identify an exoplanet in the habitable zone, we are essentially betting that it not only has the conditions to support life, but that life actually originated there. If abiogenesis is a rare event, then many potentially habitable worlds could be barren, not because they couldn't support life, but because life never started in the first place. This adds another layer of filters to the Drake equation or any similar formulation estimating the number of technological civilizations. We must consider not just the fraction of planets that are habitable, but the fraction of those where life actually arises. Our methods for detecting life remotely, such as looking for biosignatures like oxygen and methane in atmospheres, rely on life already being present and active enough to modify its environment. If a planet is habitable but uninhabited, it would not show these signs, and we might never know the difference. The origin of life is also a question of definition. At what point does a complex chemical system become alive? Is it when it can self-replicate? When it can metabolize? When it can evolve? The line is blurry, and there might be a continuum from complex chemistry to simple life forms. This grey area makes it even harder to assess the likelihood of life elsewhere. Perhaps simple prebiotic systems are common throughout the universe, existing on many worlds with liquid water and organic molecules, but they rarely make the final leap to becoming what we would recognize as a living cell. Alternatively, maybe the leap is not that difficult, and the galaxy is teeming with microbial life. We simply do not know. The search for answers continues in labs on Earth, where scientists are trying to recreate the steps of abiogenesis, and in space, where missions like those to Mars or the icy moons of Jupiter and Saturn are looking for signs of past or present life, or even just complex organic chemistry, finding even simple life elsewhere, independent of Earth. would be a monumental discovery because it would show that abiogenesis can happen more than once, dramatically increasing our estimate of life's prevalence. Conversely, if we explore many seemingly habitable worlds and find them all sterile, it would suggest that the origin of life is a major barrier. For now, the leap from inorganic matter to life remains a beautiful and profound mystery. It is the ultimate bootstrap operation, where chemistry somehow pulls itself up by its own bootstraps to create biology. This step is the foundation upon which all of evolution and complexity is built, and its potential rarity reminds us that the existence of life itself, let alone intelligent life, might be a precious and singular phenomenon in the cosmos. So, as we marvel at the conditions that make a planet habitable, we must also humbly acknowledge that habitability does not automatically grant life. It merely offers a stage. Whether the play begins is a question that only further exploration and discovery can answer. So, if life does arise on a distant world, how would we ever know? This brings us to the practical challenge of actually detecting life light years away, a task that relies on interpreting subtle clues in the light from these worlds, clues known as biosignatures. Biosignatures are substances or phenomena that provide scientific evidence of past or present life. The most sought-after biosignatures are gases in a planet's atmosphere that are out of chemical equilibrium, meaning they shouldn't coexist without a continuous biological source. The classic example is the combination of oxygen and methane in an atmosphere. On Earth, oxygen is highly reactive and would quickly combine with other elements if not constantly replenished by photosynthesis. Methane, produced by microbes and other life forms, is also rapidly destroyed in the presence of oxygen. So, finding both together in an atmosphere is a strong hint that something is actively producing them, likely biology. This is what telescopes like the James Webb Space Telescope are designed to look for. By analysing the starlight that filters through an exoplanet's atmosphere during a transit, when the planet passes in front of its star, scientists can dissect the light into a spectrum. Different gases absorb specific wavelengths of light, leaving fingerprints in the spectrum. From this, we can infer the atmospheric composition. However, this technique is incredibly challenging and has significant limitations. First, it only works for planets that transit their stars from our viewpoint, which is a small fraction of all exoplanets. Second, the signals are faint and require multiple transits to build up enough data, meaning we need to observe the same planet repeatedly over long periods. Third, our current technology is best suited for studying planets around small, dim stars like red dwarfs, because the transit depth is deeper and the signals are easier to detect relative to the star's brightness. But as we've discussed, red dwarfs are often volatile and their planets may be tidally locked and bombarded by radiation, making them less ideal for life. So, we're often studying the easiest targets, not necessarily the best ones. Even when we detect a potential biosignature, we face the problem of false positives. Nature has many ways to produce gases that look like biosignatures without any life involved. For instance, a planet with intense volcanic activity can release large amounts of methane into its atmosphere. Photochemical reactions driven by starlight can also create oxygen in certain conditions. A water-rich planet undergoing photolysis, where UV light breaks apart water molecules, can generate oxygen abiotically. Similarly, carbon dioxide can be split to produce oxygen. So, detecting oxygen alone is not proof of life. We need to look at the context. Is the oxygen in abundances that are stable over time? Are there other gases that suggest geological rather than biological processes? For example, if we see oxygen along with gases like chlorine or sulfur compounds that indicate volcanic outgassing, it might point to a false positive. Another challenge is that our models of planetary atmospheres are based on Earth, but other worlds could have very different chemistries. A planet with a different atmospheric pressure, temperature, or stellar environment might have unique abiotic pathways for producing biosignature gases. We need to understand the entire planetary system to interpret the data correctly. This includes the star's activity, the planet's geology, its potential for water, and its climate history. Without this context, a biosignature detection could be misleading. The James Webb Telescope is a powerful tool, but it's just the beginning. Future telescopes, like the Habitable Worlds Observatory, currently in planning, aim to directly image Earth-like planets around Sun-like stars, allowing for more detailed atmospheric studies. But even with advanced technology, distinguishing a true biosignature will require a comprehensive approach. Scientists are developing more robust biomarkers, such as looking for the simultaneous presence of multiple gases like oxygen, methane, DOT, and nitrous oxide, or searching for seasonal variations in atmospheric composition that might be linked to biological cycles. Another idea is to look for surface biosignatures, like the reflection of light from vegetation, but that requires direct imaging and is even more technologically demanding. The search for biosignatures is thus a game of probabilities and careful interpretation. Every potential detection will need to be scrutinized and confirmed through multiple lines of evidence. It's not enough to find a gas that could be produced by life. We must rule out non-biological explanations as much as possible. This means that the first claimed detection of life beyond Earth will likely be met with skepticism and require overwhelming evidence. The technological limits also mean that we might miss life that doesn't produce the biosignatures we're looking for. Life on other worlds could be based on different biochemistries, using solvents other than water or elements other than carbon. Such life might not produce oxygen or methane at all, and we wouldn't recognize its biosignatures with our current methods. This is why it's important to keep an open mind and develop new strategies for detection. In the end, the search for biosignatures is a testament to human curiosity and ingenuity. Despite the challenges and the risk of false clues, we continue to push the boundaries of technology and science in the hope of answering one of humanity's oldest questions. Are we alone? Each new exoplanet atmosphere we analyze brings us a step closer, but it also teaches us humility, reminding us that the universe is complex and full of surprises. So, as we await the next breakthrough, we must be patient and rigorous, knowing that the discovery of life elsewhere will change everything, but it must be built on solid, undeniable evidence. The limitations of our current technology mean that we are only scratching the surface. We can primarily study larger planets or those close to their stars, which may not be representative of the most habitable worlds. The data we get is often low resolution, making it hard to detect subtle signals. Atmospheric retrieval models are sophisticated but rely on assumptions that may not hold true for all planets. For example, clouds and hazies can obscure our view, masking the spectral features we're interested in. Even with James Webb, characterizing a true Earth analogue around a Sun-like star is beyond our current capabilities. It would require an impossibly long observation time due to the infrequent transits and the faint signal. This forces us to focus on mini-Neptunes or super-Earths around M-dwarfs, which are fascinating but might not be the best places for life as we know it. Moreover, the interpretation of biosignatures is inherently probabilistic. We use Bayesian statistics to assess the likelihood of life versus abiotic processes, but these depend on our prior expectations, which are based on a single data point. Earth. If life is common, then a detected biosignature is more likely to be biological. But if life is rare, the same signal might be deemed abiotic. This circular reasoning highlights the need for a better understanding of planetary processes across the galaxy. Another issue is the temporal dimension. A biosignature might be detectable only during certain seasons or geological eras. If we observe a planet at the wrong time, we might miss the signs. Conversely, A transient abiotic event, like a massive volcanic eruption, could create a temporary biosignature-like signal that disappears, leading to confusion. The search is further complicated by interstellar medium effects and instrumental noise, which can introduce artifacts or obscure real features. To overcome these hurdles, the astrobiology community is advocating for a multi-pronged approach. This includes studying extreme environments on Earth to understand the limits of life and the range of possible biosignatures, developing new telescopes with higher sensitivity and stability, and creating advanced algorithms to model exotic atmospheres. Collaboration across disciplines, astronomy, geology, chemistry, and biology is essential. The goal is to build a framework where a potential biosignature can be evaluated against a full suite of planetary data, including its orbit, stellar flux, dot, geological activity, and even potential biosignatures on its surface or in its oceans. For now, every detection is a learning opportunity. Even false positives teach us about planetary diversity and help refine our models. The journey to find life is as much about understanding planets and stars as it is about biology. It forces us to question our assumptions and broaden our perspectives. While the technological limits are real, they are not permanent. Each generation of instruments brings new capabilities, and with them, new hopes. The dream of finding another living world drives innovation and inspires us to look deeper into the cosmos. So, as we continue this great search, we do so with caution, but also with excitement, knowing that every observation could be the one that reveals we are not alone. The path is fraught with false clues and technological barriers, but the potential reward, a confirmed sign of life beyond Earth, is worth every challenge. Considering all the immense challenges in even detecting signs of life, from technological limits to deceptive false positives, it's worth stepping back and asking a more fundamental question. What if complex life is just extraordinarily rare in the universe? This line of thinking is crystallized in what scientists call the rare Earth hypothesis, a compelling argument that suggests planets like Earth, teeming with diverse and intelligent life, might be the exception rather than the rule. The core idea is that a specific and incredibly improbable series of events and conditions had to align perfectly for life to advance beyond simple microbes to the complexity we see around us. It's not necessarily that life itself is rare. Microbial life could be relatively common throughout the cosmos, floating in the clouds of gas giants or buried deep in the ice of frozen moons. But the jump to multicellular organisms, let alone technological civilizations, might require a checklist of factors so long and demanding that very few worlds ever meet all the criteria. Think about everything we've explored so far. A planet needs to be in the habitable zone of a stable, long-lived star, like our Sun, which is already less common than the turbulent red dwarfs that dominate the galaxy. That planet must have a nearly circular orbit to avoid extreme temperature swings, and it needs a large moon to stabilize its axial tilt, preventing chaotic climate variations that would regularly wipe out evolving ecosystems. This moon likely formed from a random dot, violent collision early in the solar system's history, an event that might not be common elsewhere. Then, the planet itself must be geologically active, with plate tectonics recycling carbon and nutrients while regulating the global temperature over billions of years. It requires a powerful magnetic field generated by a molten, spinning core to shield its atmosphere from being stripped away by stellar winds. The atmosphere must have the exact right composition, a delicate balance of greenhouse gases to maintain liquid water, but not so much as to trigger a runaway greenhouse effect like on Venus. It needs a protective ozone layer to filter out harmful ultraviolet radiation while allowing visible light through for photosynthesis. The planetary system must be architecturally sound, with a giant gas giant like Jupiter in just the right position to act as a gravitational shield, deflecting comets and asteroids without destabilizing the inner planet's orbits. The planet must also have the right amount of water, delivered by comets or asteroids, but not in such excess that it becomes a water world with no continents or nutrient cycling. Its rotation speed must be just right to generate a magnetic field and maintain a balanced day-night cycle. It must avoid nearby supernovae or gamma-ray bursts that could sterilize its surface. And even with all these physical and astronomical factors in place, life still has to originate from non-living matter, a process called abiogenesis that we don't fully understand, and that might be a severe bottleneck in itself. Then, that life must survive for billions of years without being wiped out by a supervolcano, an ice age, or an impact event. It must navigate the evolutionary leap from single-celled to multicellular organisms, which on Earth took over 2 billion years, and then develop intelligence and technology, which is another gamble influenced by countless random events. The rare Earth hypothesis posits that the probability of all these conditions being met on a single world is astronomically low. Earth isn't just a standard rocky planet in a habitable zone, it's a cosmic winner, a planet that hit the jackpot in a lottery with odds stacked overwhelmingly against it. This perspective challenges the Copernican principle, the idea that there's nothing special about our place in the universe. Instead, it suggests that for complex life, we might be in a very special place indeed. If this hypothesis is correct, then the silence we hear from the cosmos, the fact that we haven't found any signs of extraterrestrial intelligence, isn't due to a lack of trying or technological limitations, but simply because there is no one else out there to talk to, at least not within communicative range. Microbial life might be scattered across the galaxy, thriving in subsurface oceans or extreme environments, but worlds with forests, animals, and civilizations could be separated by vast, empty distances, making the universe feel largely barren from our perspective. This isn't a pessimistic view, but a humbling one. It forces us to appreciate the incredible series of fortuitous accidents that led to our existence. Every time we look at the moon, we should remember its role in keeping our climate stable. Every time we feel the ground shake from tectonic activity, we should appreciate the planetary thermostat that regulates our long-term climate. The oxygen we breathe is a direct product of billions of years of biological activity, sustained by a protective magnetic field and a calm star. This realization also carries a profound responsibility. If Earth is truly a rare oasis in a cosmic desert, then its preservation becomes paramount. The biodiversity and ecosystems that took eons to develop are not just valuable for us, but might be unique in the entire galaxy. The rare Earth hypothesis adds weight to the argument for environmental conservation. We are custodians of a world that against all odds became a haven for complex life. Of course, this is still a hypothesis, and it has its critics. Some scientists argue that life is incredibly resilient and adaptable, and that given the vast number of planets, the same conditions could have arisen elsewhere. They point to extremophiles on Earth that survive in conditions once thought uninhabitable, suggesting that life could find a way in environments we haven't even imagined. Perhaps intelligence evolves through different pathways, or maybe other biochemistries are possible. The universe is a big place, and with trillions of stars, even a very low probability event might happen multiple times. However, the sheer number of filters and the specificity of each requirement make a strong case for rarity. As we discover more exoplanets, we are gathering data to test this idea. If we find many Earth-like worlds with similar conditions and biosignatures, the hypothesis would be weakened. But if, after extensive searching, we find that most habitable zone planets are barren, tidally locked, or lacking key features like a magnetic field or plate tectonics, It would support the notion that Earth is special. For now, the evidence from our own solar system is telling. Mars had water and a thicker atmosphere once, but lost its magnetic field and became a desert. Venus is a hellish greenhouse with no plate tectonics to regulate its climate. The giant planets are gaseous and hostile. The icy moons might host microbes, but complex life seems unlikely. So, while we should continue searching with optimism and curiosity, we must also consider the possibility that we are alone, not just in our galaxy, but in the observable universe. This doesn't diminish our significance. It amplifies it. We are the universe's way of understanding itself, a flicker of consciousness in the vast cosmic dark. The rare Earth hypothesis reminds us that our planet is a precious gem, a fragile bubble of life that has endured against improbable odds. It encourages us to look outward to the stars with wonder, but also to look inward and protect the only home we've ever known. The silence from space might not be an empty void, but a message that what we have here is rare, beautiful, and worth preserving for all the future generations that may never find another world like it. So, as we advance our technology and reach further into the cosmos, let's carry this perspective with us, fueling both our exploration and our stewardship of this pale blue dot we call Earth. But if Earth-like planets are so rare, where else could we possibly look for life? This is where our search expands beyond the traditional habitable zone to some of the most fascinating worlds in our own solar system, the icy moons of gas giants. We've been fixated on planets orbiting at just the right distance from their stars, but life might not care about starlight at all if it has another source of energy and liquid water. Imagine a world covered in a thick dot, global shell of ice, so far from the sun that sunlight is just a dim star in a perpetually dark sky. Beneath that icy crust, however, could lie a vast, dark ocean, kept liquid not by the warmth of a star, but by the relentless gravitational tug-of-war of a giant planet. This is the reality for moons like Jupiter's Europa and Saturn's Enceladus, and they represent a completely different paradigm for habitability, one that challenges our Earth-centric view. These moons are not in the habitable zone. They are in the frozen outer reaches of the solar system, where surface temperatures are hundreds of degrees below zero. Yet, scientists are incredibly excited about them because they are considered prime candidates in the search for extraterrestrial life. The key to their potential lies in internal heat generated by tidal forces. As these moons orbit their massive parent planets, the planet's immense gravity flexes and stretches them. This constant gravitational squeezing generates friction deep within the moon's interior, producing enough heat to melt ice and maintain global subsurface oceans. This process is so effective that Europa, for instance, is thought to have an ocean containing more than twice the volume of all Earth's oceans combined, hidden beneath an ice shell that might be several miles thick. Enceladus, a much smaller moon, has geysers that erupt from fissures in its icy surface, spewing water vapour, ice particles, and organic molecules into space, providing direct samples from its subsurface sea. This means we don't necessarily have to land and drill through the ice. We can fly a spacecraft through these plumes and analyse their composition. The discovery of complex organic molecules in these plumes is a huge deal because it shows that the basic chemical ingredients for life are present and being actively processed. Now, the kind of life that could exist in these dark, underwater environments would be fundamentally different from most life on Earth. Without sunlight, photosynthesis is impossible. Instead, any ecosystem would have to be based on chemosynthesis, a process where organisms derive energy from chemical reactions. On Earth, we see this in deep-sea hydrothermal vents on the ocean floor, where superheated, mineral-rich water spews from the Earth's crust. Bacteria, they use chemicals like hydrogen sulfide as an energy source to produce organic matter, forming the base of a food web that includes giant tube worms, clams, and bizarre crustaceans. Similarly, on Europa or Enceladus, hypothetical hydrothermal vents on the seafloor could provide the energy and nutrients for microbial life, which could in turn support more complex organisms. The water in these oceans is likely in contact with a rocky mantle, allowing for the same kind of water-rock interactions that are crucial for life on Earth. This provides a pathway for essential elements like phosphorus, sulfur, DOT, and potassium to dissolve into the water, creating a nutrient-rich broth. However, habitability on these moons comes with its own set of challenges. The ice shell itself is a barrier. It blocks sunlight and protects the ocean from the harsh radiation environment around gas giants like Jupiter, but it also makes the surface inhospitable and difficult to access. The thickness of the ice is a critical factor. If the ice is too thick, it might prevent the exchange of materials between the ocean and the surface, potentially leading to a stagnant, chemically depleted environment. If it's too thin, the ocean might be exposed to radiation or lose heat too quickly. Orbital stability is another concern. These moons need to maintain a stable orbit around their planet to ensure consistent tidal heating. If their orbits become too eccentric, or if they are influenced by other moons, the tidal heating could vary, leading to freezing or extreme geological activity. The presence of an energy source is not guaranteed everywhere. It depends on the specific orbital resonances with other moons. For example, Io, another moon of Jupiter, is the most volcanically active body in the solar system due to intense tidal heating, but it has no water and is far too hot for life as we know it. So, the tidal heating needs to be just right, strong enough to maintain liquid water but not so strong as to boil the ocean or tear the moon apart. Another challenge is the availability of key elements for life, such as carbon, hydrogen, DOT, nitrogen, oxygen, phosphorus, and sulfur. While the plumes of Enceladus have shown us that organic molecules are present, we don't yet know if all the necessary building blocks are there in sufficient quantities and in forms that life can use. The pH and salinity of the ocean also matter. If the water is too acidic or too salty, it could inhibit biochemical reactions. Furthermore, the pressure at the bottom of these deep oceans could be immense, potentially crushing life forms that aren't adapted to such conditions. Despite these challenges, the potential for life on these moons is so compelling that space agencies are planning dedicated missions. NASA's Europa Clipper mission, set to launch in the coming years, will conduct detailed reconnaissance of Europa's ice shell and subsurface ocean, mapping the thickness of the ice and searching for signs of recent activity. Even more ambitious are concepts for landers that could drill or melt through the ice to directly sample the ocean. Though that technology is still in development, the exploration of these ocean worlds forces us to broaden our definition of habitability. We can no longer think of the habitable zone as a narrow band around a star. Instead, we must consider a habitable system where tidal forces, geological activity, and chemical energy can create oases of life in the cold outer darkness. This expands the number of potential habitats in our galaxy exponentially. Think about it. While sun-like stars might be rare, gas giants are common, and many of them likely have icy moons. If even a small fraction of those moons have subsurface oceans with the right conditions, the galaxy could be filled with hidden biospheres, completely isolated from each other and from the light of their stars. This possibility is both exciting and humbling. It suggests that life might be more widespread than we thought, but it also might be mostly microbial, hidden away in dark oceans, never developing technology or becoming visible to us. The search for life on these moons is not about finding intelligent civilizations. It's about finding any life, even simple microbes, which would revolutionize our understanding of biology and our place in the universe. Finding life independently arisen on Europa or Enceladus would tell us that life is not a fluke confined to Earth, but a natural and common process in the cosmos. It would mean that the universe is biologically active, even if silently so. So, as we continue to scan the skies for Earth-like exoplanets, we must also turn our gaze closer to home, to the frozen moons in our own backyard. They represent a different path to habitability, one that doesn't rely on the warmth of a star, but on the gravitational dance of planets and moons. This journey of discovery is just beginning, and each new mission brings us closer to answering the age-old question, are we alone? The icy shells of Europa and Enceladus might hide the answer, waiting in the dark, quiet waters beneath the ice, while the icy moons of the outer solar system present a compelling case for life in isolated oceans. The story of how Earth itself became a water-rich world capable of fostering life is tied to a violent and chaotic period in our solar system's history known as the Late Heavy Bombardment. This was a time, around 4 billion years ago, when the inner planets were subjected to a dramatic increase in the rate of asteroid and comet impacts. The surfaces of the Moon, Mercury, Dot, and Mars still bear the craters from this ancient onslaught, a visible record of a truly destructive era. It seems counterintuitive that such a cataclysmic event could be beneficial, but this period of intense punishment may have been absolutely crucial for delivering the very ingredients necessary for life to eventually emerge on our planet. The early Earth, after its initial formation, was likely a hot, molten world, and any original water or organic molecules would have been boiled away into space. As the planet cooled and a solid crust formed, it was essentially a dry and relatively barren rock. The water that now fills our oceans and the complex organic molecules that form the basis of life had to come from somewhere else. The most likely delivery vehicles were the countless comets and asteroids that rained down during the late heavy bombardment. Comets, often described as dirty snowballs, are rich in water ice, along with frozen gases like carbon dioxide, ammonia, DOT, and methane. When they collided with the early Earth, their ice would have vaporized upon impact, eventually condensing and falling as rain, gradually filling the basins that became our oceans. Asteroids, DOT, particularly a type known as carbonaceous chondrites, are also packed with water bound within clay minerals and are incredibly rich in complex organic compounds, including amino acids and nucleobases, which are the fundamental building blocks of proteins, and DNA, analyses of meteorites that have fallen to Earth in modern times, confirm that these materials form naturally in space, through reactions on dust grains in interstellar clouds or within the asteroids themselves. So, each impact during this bombardment was like a cosmic delivery truck, bringing in parcels of water and prebiotic chemistry from the outer solar system. This concept is known as panspermia, though in this case, it's the building blocks of life that are being spread, not life itself. Without this external delivery service, Earth might have remained a dry, lifeless world, lacking the volatile compounds and water essential for biochemistry. However, the bombardment presents a profound paradox, a delicate balance between creation and destruction. While these impacts were bringing the ingredients for life, they were also releasing immense amounts of energy, enough to vaporize oceans and sterilize the planet's surface repeatedly. An impact from a large enough asteroid or comet could have boiled off the entire ocean and melted the crust, effectively resetting the clock for life any time it tried to get started. This is the Goldilocks problem of the late heavy bombardment. It couldn't be too weak, or the planet would not receive enough water and organics, but it also couldn't be too strong, or it would continuously wipe out any nascent life. The intensity and timing had to be just right. a period of moderate bombardment that delivered the necessary materials, followed by a relatively rapid decline in impact frequency, would have provided the perfect window. The ingredients would have been delivered, and then the environment would have stabilized enough for those ingredients to slowly assemble into more complex structures in the newly formed oceans and ponds. The cause of the late heavy bombardment itself is a subject of active research. The leading theory, known as the Nice model, suggests that the giant planets Jupiter, Saturn, Uranus, and Neptune underwent a gravitational dance, migrating from their original orbits. This planetary migration would have destabilized a vast reservoir of asteroids and comets in the outer solar system, sending a shower of them inward toward the Sun, where they collided with the inner planets. If this model is correct, then the delivery of water and organics to Earth was a direct consequence of the dynamic evolution of our entire planetary system. This implies that not every planetary system will experience such an event. In some systems, the giant planets may remain in stable orbits from the beginning, never triggering a heavy bombardment. In others, the bombardment might be too severe or too prolonged, preventing life from ever gaining a foothold. The fact that Earth experienced a bombardment that was intense enough to deliver the goods but brief enough to allow recovery might be another critical factor in our planet's habitability. The evidence for this period is written on the Moon. The lunar highlands are heavily cratered, and rock samples brought back by the Apollo missions have been dated to around this time, forming a cluster of ages that suggest a spike in impacts. Because the Moon is geologically inactive, it preserves this ancient record, which has been largely erased on Earth by plate tectonics and erosion. Studying the Moon helps us understand what Earth must have endured. This concept also expands the potential habitats for life. Icy moons like Europa and Enceladus would have also been bombarded, potentially receiving organic-rich material from the outer solar system. In their case, the impacts might have delivered the chemicals directly onto their icy surfaces, which could then be transported downward to the subsurface oceans through geological processes or by the impacts themselves punching through the ice. So, the late heavy bombardment might have been a system-wide event that seeded multiple worlds with the ingredients for life. The timing is also crucial. On Earth, the earliest evidence for life appears in rocks not long after the bombardment period ended. This suggests that life got started relatively quickly once the conditions stabilized, which in turn implies that the emergence of life might be a fairly probable process once the right ingredients are in place in a suitable environment. However, if the bombardment had continued for much longer, it could have snuffed out life repeatedly, or if it had been too weak, Earth might have remained a desert planet. This balance is yet another filter in the long chain of events leading to a habitable world. When we look at other planetary systems, we have to consider their impact history. A system with a different arrangement of giant planets might not have a mechanism to deliver water and organics to the inner rocky worlds, or the delivery might happen too early, before the planets have cooled and formed stable crusts, causing the volatiles to be lost to space. The late heavy bombardment reminds us that a planet's habitability is not just about its current state, but also about its history. It is a story of cosmic violence and cosmic generosity, a period where destruction and creation were two sides of the same coin. The water we drink and the molecules that make up our bodies were forged in the depths of space and delivered to our planet in a fiery rain billions of years ago. This shared cosmic heritage connects us not only to the other worlds in our solar system, but to the galaxy at large. As we search for life beyond Earth, we are implicitly searching for worlds that have also passed through this trial by fire, receiving the gift of water and organics without being utterly destroyed by the process. It is a narrow path to walk, and another reason why the universe might be quiet, with life being a rare and precious outcome of a very specific and violent cosmic history. Even if life successfully emerges on a world, Having navigated the chaotic delivery of water and organics in the precarious early environment, the journey towards the kind of complexity we see on Earth is far from guaranteed. This is the next great filter, the evolution of complexity itself. The vast majority of Earth's history was dominated by single-celled organisms. For over 2 billion years, life remained stubbornly microbial, a world of bacteria and archaea thriving in the oceans. The leap to multicellularity, where cells specialize and cooperate to form a single, larger organism, was a monumental evolutionary transition that happened only once in the grand scheme of life on our planet, and it took an immense amount of time. This suggests that this step is not an inevitable progression, but a difficult bottleneck, a barrier that many biospheres might never cross. The advantages of being multicellular are clear from our perspective. It allows for larger size, specialization of cells into tissues and organs, and the ability to exploit new ecological niches. But the evolutionary pressures to make this leap must be significant. It requires a shift in the fundamental unit of selection from the individual cell to the collective organism. Cells must forego some of their own reproductive potential for the benefit of the whole, a cooperation that can be unstable and vulnerable to cheating from within, where mutant cells might replicate uncontrollably, effectively becoming cancer. For multicellularity to arise and persist, there must be a strong selective advantage that outweighs these risks. On Earth, this may have been driven by factors like predation, where being larger provided a defense, or by the need to remain anchored in a favorable spot in a photic zone, requiring a larger, more complex structure. But these conditions are not universal. A planet with a very stable, unchanging environment might not provide the necessary pressure for such a radical innovation. Life might remain perfectly adapted as simple, single-celled forms for billions of years, never feeling the need to become more complex. Furthermore, the genetic and developmental machinery for multicellularity is intricate. It requires sophisticated systems for cell adhesion, communication, and programmed cell death. The evolution of these systems might depend on rare genetic events, such as the incorporation of viral DNA or specific symbioses between different types of microbes. If the probability of such events is low, then the galaxy could be filled with worlds where life exists, but only as a microbial slime, never progressing to plants, animals, or anything we would readily recognize as complex. Then, even if multicellular life does arise, the development of intelligence and technology represents another formidable bottleneck. Intelligence, as we define it, is not the pinnacle of evolution, but merely one survival strategy among many. On Earth, it has only appeared once in a dominant form. Many animal groups have developed notable intelligence: octopuses, dolphins, corvids, and primates. But only one lineage has developed technology capable of altering the planet and reaching for the stars. This suggests that the evolutionary path to technological intelligence is narrow and contingent on a specific set of circumstances. What are some of these prerequisites? One is a certain level of sensory and manipulative capability. For a species to develop technology, it helps immensely to have limbs that can grasp and manipulate objects with precision. Like hands or tentacles, it also requires sophisticated sensory input, particularly vision, to perceive the world in high detail and model cause and effect. But physical form is only part of the story. The social and ecological context is equally critical. Intelligence often flourishes in socially complex species where there is an advantage to outsmarting competitors, cooperating in hunts, or navigating intricate group dynamics. The cognitive arms race within a social group can drive the development of larger brains and greater problem-solving abilities. However, a large brain is an extremely expensive organ to maintain, consuming a huge amount of energy. For natural selection to favour such an investment, the benefits must significantly outweigh the costs. A species living in a resource-poor environment or one with few predators might never evolve large brains because the energy expenditure isn't justified. The existence of a niche for intelligence is also key. For most of Earth's history, the dominant animals were not particularly intelligent by our standards. The dinosaurs ruled the planet for over 100 million years without any species developing technology. It was only after a catastrophic asteroid impact cleared the way that small, nocturnal, socially complex mammals had the opportunity to radiate and eventually fill the niche that led to us. This implies that intelligence might require a trigger, a shake-up of the ecosystem that creates an opening for a new survival strategy. Furthermore, the development of technology requires a stable period long enough for knowledge to accumulate and be passed down through generations. A species constantly on the brink of extinction due to climate volatility, supervolcanoes, or frequent impacts would not have the leisure to experiment with tool use, fire, and language. The planet must provide a long, stable window for cultural and technological evolution to occur. Language, symbolism, and the ability to abstractly represent the world are themselves huge evolutionary leaps. The emergence of cumulative culture, where each generation builds upon the knowledge of the last, is a powerful accelerator, but it is not a given. Many intelligent species on Earth use tools and have complex social structures, but only one has developed written language and the scientific method. The combination of all these factors, the right physical form, the right social structure, the right ecological niche, the right planetary stability, and the right cognitive capabilities, may be exceptionally rare. It is perfectly plausible, and perhaps even likely, that the galaxy is teeming with worlds where life exists, but it is mostly microbial. On a smaller number of worlds, multicellular life may have arisen, filling the oceans with complex algae and the land with simple plants and perhaps even animal-like creatures. But on only a handful of worlds, if any besides Earth, would that complexity have ever culminated in a species that looks at the stars and wonders about its place in the cosmos. The evolution of intelligence and technology might be the rarest step of all. This perspective, often called the Great Filter hypothesis, suggests that the silence we hear from the universe might be because most life never gets to the stage of building radio telescopes or spaceships. They are forever trapped in a pre-technological state, or they go extinct before they can make their presence known on a galactic scale. This is not a pessimistic view, but a realistic one that helps frame the Fermi paradox. The vast timescales involved also work against us. Technological civilizations might be ephemeral, blinking in and out of existence in a cosmic instant, separated by millions of years of silence, making the chance of two such civilizations overlapping in time incredibly small. So, as we search for biosignatures in exoplanet atmospheres, we are primarily searching for signs of any life, most likely microbial. Finding evidence of complex, multicellular life would be a staggering discovery, indicating that at least one major bottleneck has been overcome. But finding evidence of intelligence? That would be the ultimate discovery, telling us that our particular journey from microbe to stargazer is a path that the universe can take more than once. Until then, we must consider that the evolution of complexity, and especially intelligence, might be the final and most formidable filter in the long chain of events that leads from a sterile planet to a civilization capable of asking these very questions. So, while the evolution of intelligence is one potential bottleneck, the very star a planet orbits presents a constant and dynamic threat that can sterilize a world long before complexity ever has a chance to arise. This brings us to the formidable challenge of stellar variability, particularly the devastating power of superflares. We often think of stars as steady, reliable sources of light and heat, but many stars, especially the most common type in the galaxy, are prone to violent tantrums that can fundamentally alter the fate of any orbiting planets, red dwarf stars, or M-dwarfs, which make up about 3/4 of all stars in the Milky Way, are notoriously unstable. Their habitable zones are located very close in due to their low luminosity, but this proximity comes with a terrible cost. These stars are frequently racked by massive stellar flares, sudden and explosive releases of magnetic energy that can, in a matter of minutes, unleash the energy of billions of atomic bombs. For a planet huddled close to its dim star to stay warm, this onslaught of radiation is a constant existential threat. When one of these superflares erupts, it bathes the nearby planet in an intense wave of X-rays and ultraviolet radiation. This radiation doesn't just deliver a momentary blast, it can have long-term catastrophic effects. The high-energy UV radiation can break apart molecules in the atmosphere, including water vapor, leading to the loss of hydrogen to space and a potential runaway greenhouse effect if the planet cannot hold onto its water. The X-rays can heat and inflate the upper atmosphere, increasing the rate of atmospheric escape. Over time, repeated flaring can strip away a planet's atmosphere entirely, leaving it a barren rock, much like Mars, but on a much faster timeline. Furthermore, this radiation directly assaults the surface. It can break down complex organic molecules that are the precursors to life, and it would be lethal to any life forms that are not deeply shielded underground or underwater. For a planet tidally locked to a red dwarf, with one hemisphere permanently facing the star, the constant flare activity would make the surface utterly uninhabitable, scorching the day side and potentially destroying any protective ozone layer repeatedly. But the danger is not confined to red dwarfs alone. Even stars like our Sun have a history of greater activity. In its youth, the Sun was likely more volatile, rotating faster and generating a stronger magnetic field, which would have led to more frequent and powerful flares. The young Earth, with a thinner atmosphere and a weaker magnetic field, would have been vulnerable to this heightened stellar activity. It is possible that life's early attempts to establish itself were repeatedly set back by these solar outbursts, until the planet's defences, a thicker atmosphere and a robust magnetic field, were able to provide adequate protection. The key for any planet is its ability to weather these stellar storms. A strong, global magnetic field is the first line of defence, acting as a shield that deflects the charged particles of the stellar wind and the most energetic particles from flares, channeling them towards the poles and creating auroras instead of allowing them to batter the atmosphere. A thick atmosphere is the second critical buffer. It absorbs and scatters the harmful UV and X-ray radiation, preventing most of it from reaching the surface. Atmospheres with a significant ozone layer are particularly effective at blocking UV. However, a superflare from a close-in star can be so powerful that it can overwhelm these defences. It can ionize the upper atmosphere, creating a conductive layer that can short-circuit a planet's magnetic field and allow more energy to penetrate. It can also trigger chemical reactions that destroy ozone, leaving the surface exposed to subsequent UV radiation for months or years after the flare itself has subsided. The frequency of these events is also crucial. A planet might survive an occasional superflare if it has time to recover, but if the flares are a weekly or even daily occurrence, as they can be on some active red dwarfs, there is no opportunity for recovery. The atmosphere would be in a constant state of erosion, and the surface would be repeatedly sterilized. This makes the search for life around red dwarfs particularly challenging. While they are abundant and their planets are easier to detect, their violent nature may render most of them uninhabitable. When we look for planets in the habitable zone, we must therefore consider not just the star's current luminosity and temperature, but its activity and age. An older red dwarf may have calmed down, its rotation slowed by billions of years, resulting in a much quieter stellar environment. Finding a planet in the habitable zone of a quiescent, older red dwarf might be one of our best bets for finding a stable world. However, determining a star's activity level and flare history from light years away is a difficult task. We can monitor stars for brightness variations that indicate spots and flares, but a long period of observation is needed to characterize their true temperament. This stellar variability adds another layer to the habitability checklist. A planet must not only be in the right place, but its star must also have the right personality, a stable, calm disposition that allows for billions of years of peaceful evolution. The threat of superflares reminds us that habitability is not a static condition, but a dynamic balance between a planet's defenses and its star's aggression. A world with a weak magnetic field and a thin atmosphere, no matter how perfectly positioned in the habitable zone, would be a sitting duck, its potential for life extinguished by the very star that gives it light and warmth. This is yet another filter that narrows the field of potential abodes for life. As we continue to discover exoplanets, we are learning to categorize stars not just by their type and size, but by their activity. We are starting to understand that a quiet, middle-aged star like our Sun might be a far safer harbour for life than a more common, but tempestuous, red dwarf. The cosmic silence might therefore be explained in part by the fact that the most common stellar real estate in the galaxy is also the most dangerous, and that truly stable, long-lived stars with well-protected planets in their habitable zones are a precious commodity. Our Sun's relative calm is not a given. It is a feature that has allowed life on Earth the stability to flourish, and it is a feature we must seek out if we hope to find life elsewhere. But even with a calm and stable star providing consistent energy, a planet's own internal dynamics and orientation play a huge role in determining whether it can support life. And one of the most underappreciated yet vital factors is its axial tilt. This is the angle between the planet's rotational axis and a line perpendicular to its orbital plane around the star. For Earth, this tilt is about 23.5 degrees, and it is the reason we have seasons. As our planet travels around the Sun, this tilt causes different hemispheres to lean towards or away from the Sun at different points in the orbit, leading to the cyclical changes in temperature and daylight hours that we experience as spring, summer, autumn, and winter. These seasons are not just a backdrop for our calendars, they are a fundamental mechanism for distributing solar energy across the globe. Without this tilting, the poles would be perpetually cold and the equator intensely hot. But the seasonal shift helps to moderate these extremes by allowing higher latitudes to warm up during their summer and cool down during their winter. This dynamic energy distribution is crucial for maintaining a relatively stable global climate and is a key driver of biodiversity. The varying conditions encourage migration, hibernation, and other adaptations, fostering a rich tapestry of life that can exploit different niches throughout the year. However, the mere existence of a tilt is not enough. Its stability over geological time is absolutely critical. Earth's tilt does wobble slightly in cycles over tens of thousands of years, but these variations are small and predictable, thanks largely to the gravitational influence of our Moon. The Moon acts as a stabilizer, its gravity exerting a torque that dampens any potential wild swings in Earth's orientation. Without our disproportionately large lunar companion, Earth's axial tilt could become chaotic, varying by dozens of degrees over millions of years. We can see a stark example of this in our solar system with Mars. Mars has two very small moons, Phobos and Deimos, which are too tiny to provide any significant stabilizing effect. As a result, Mars's axial tilt is known to vary dramatically, with shifts of up to 60 degrees possible over time. Such extreme variations would have catastrophic consequences for climate stability. Imagine a world where the tilt changes so much that the polar regions could effectively swap places with the tropics. Ice caps would form at the equator, while deserts appeared at the poles. The climate would be in constant, violent flux, with temperature swings so severe that any long-term ecosystem would be impossible to maintain. Life might struggle to survive such upheavals, let alone evolve into complex forms. On the other hand, consider a planet with virtually no axial tilt. Such a world would have no seasons at all. The amount of sunlight received at any given latitude would be constant throughout the year. While this might sound peaceful, it would likely lead to stagnant and extreme weather patterns. The equator would be a permanent, blistering hot zone, with intense solar radiation creating a vast, arid desert. The poles would be locked in eternal cold, with ice caps that never retreat. The middle latitudes might have a more moderate climate, but without seasonal changes, atmospheric circulation patterns could become fixed and monotonous. This lack of dynamism would severely limit the planet's ability to distribute heat and moisture efficiently. Ocean currents might weaken, and weather systems could become predictable to the point of stagnation. For life, this could be a dead end. Seasonal changes often trigger biological events like breeding, flowering, and migration. Without these cues, ecosystems might lack the diversity and resilience needed to adapt to long-term changes. The evolution of complex life could be stifled in such an unchanging environment. Therefore, the value of the axial tilt itself is also important. A tilt too extreme, say over 40 degrees, would create seasons of such intensity that they could be devastating. Summers would be scorchingly hot, and winters bitterly cold, potentially leading to repeated freezes and thaws that could disrupt life cycles. A tilt too shallow, as mentioned, eliminates seasons altogether. Earth's tilt of around 23 degrees seems to be in a sweet spot, producing noticeable but manageable seasons that foster biodiversity without causing overwhelming stress. The stability of this tilt, enforced by the moon, cannot be overstated. The moon's steadying hand has likely been a key factor in allowing Earth's climate to remain stable enough over billions of years for life to not only emerge, but to flourish and diversify. This requirement for a large moon adds another layer to the habitability puzzle. As we've discussed, the formation of such a moon is thought to be the result of a rare and violent giant impact early in Earth's history. Not all rocky planets will have such a companion. Many may have no moon at all, or only small captured asteroids that cannot provide gravitational stabilization. When we look for exoplanets, we must consider this aspect. A planet might be in the habitable zone of a quiet star, have a protective magnetic field, and even have plate tectonics, but if its axial tilt is unstable, its climate could be too chaotic for complex life. Alternatively, if its tilt is zero, its climate might be too stagnant. We have no direct way to measure the axial tilt of exoplanets yet, but we can infer potential stability from the presence of large moons, which might be detectable through future telescopes by observing their gravitational effects on the planet's orbit or through direct imaging. The interplay between axial tilt, orbital eccentricity, dot, and other factors is complex. For instance, a planet with a highly elliptical orbit would have strong seasonal variations even with zero tilt, as its distance from the star changes dramatically, but such orbits are often unstable and can lead to extreme temperature swings that are detrimental to life. A circular orbit with a stable, moderate tilt seems to be the ideal combination for a temperate world. The story of axial tilt reminds us that habitability is a delicate balance of many factors, both internal and external. A planet must not only be in the right place but also be oriented and stabilized in the right way. The silent, constant influence of our moon, often taken for granted, is a guardian of our climate, ensuring that the seasons turn predictably and that the planet remains a hospitable home. as we search for other Earths, we must add stable axial tilt to our growing list of requirements, knowing that each new filter makes the candidate pool smaller. The cosmic silence might be due in part to the fact that many worlds are either tilted chaotically or not at all, rendering them unable to support the long-term, stable environments that complex life requires. So, the next time you enjoy the change of seasons, remember that it's a sign of a planet that is not just habitable, but optimally tuned for life, a rare gem in a cosmos full of worlds that may be too wild or too still to ever echo with the sounds of a thriving biosphere. The stability provided by a consistent axial tilt is a gift, but it would mean very little without a powerful, long-term mechanism to regulate the planet's temperature against various external and internal pressures. This is where one of Earth's most brilliant and intricate systems comes into play: the carbon-silicate cycle, a geological thermostat that operates on million-year timescales to keep the climate within a range that allows for liquid water. It is a negative feedback loop of stunning elegance, a self-correcting process that links the atmosphere, the oceans, the rocky continents, and the planet's molten interior. The cycle begins with the atmosphere. Carbon dioxide, a key greenhouse gas, traps heat and warms the planet. This warmth, combined with water, is essential for driving the chemical weathering of silicate rocks on the continents. Rainwater, which is slightly acidic because it has dissolved CO2 from the atmosphere, falls onto rocks like granite and basalt. This chemical reaction slowly breaks down the silicate minerals, and the resulting dissolved products, calcium ions and bicarbonate ions, are washed by rivers into the oceans. Once in the ocean, marine organisms, such as plankton and corals, use these ions to build their shells and skeletons out of calcium carbonate. When these organisms die, their carbonate shells sink to the deep ocean floor, forming layers of sediment. This process effectively locks away carbon dioxide from the atmosphere into the solid rock of the ocean crust. But the cycle doesn't end there. This is where plate tectonics provides the crucial return mechanism. The oceanic plates, with their layers of carbonate-rich sediment, are constantly moving. Eventually, they are subducted, sliding back into the Earth's hot mantle at tectonic boundaries. The immense heat and pressure at depth cause the carbonate minerals to break down, releasing the stored carbon dioxide. This CO2 then makes its way back to the surface through volcanic eruptions, completing the loop. The beauty of this cycle is its built-in stability. If the planet gets too warm, for instance from an increase in volcanic outgassing, the higher temperatures lead to more evaporation and more rainfall. This accelerated rainfall speeds up the chemical weathering of rocks, pulling more CO2 out of the atmosphere. With less greenhouse gas, the planet cools down. Conversely, if the planet gets too cold, perhaps heading towards a global glaciation, the lower temperatures slow down chemical weathering. Meanwhile, volcanoes continue to pump CO2 into the atmosphere. With less weathering to remove it, the CO2 levels gradually build up, enhancing the greenhouse effect and warming the planet back up. This exquisitely balanced feedback has kept Earth's climate relatively stable for billions of years, even as the sun's output has steadily increased. It is the reason we are not a frozen ball of ice or a scorching greenhouse like Venus. For this cycle to function, however, a planet must meet several non-negotiable conditions. First, it must have liquid water on its surface to drive the chemical weathering process. A frozen world or a dry world cannot weather its rocks effectively. Second, it must have active plate tectonics to recycle the carbon from the ocean floor back into the atmosphere through volcanism. A geologically dead planet, like Mars, might have had weathering in the past, but without the return ticket for the carbon, the cycle grinds to a halt and the atmosphere can be lost. Third, the planet needs to have continents, exposed silicate rocks for weathering to occur efficiently. A water world, completely covered by a deep ocean, might have very limited weathering, potentially leading to a buildup of CO2 and a runaway greenhouse effect. The presence of life also plays a significant role in accelerating this cycle. Plant roots and microbial activity in soils can greatly enhance the weathering rate of rocks, making the biological and geological systems deeply intertwined. The carbon silicate cycle is therefore not just a geological curiosity. It is a fundamental prerequisite for long-term habitability. It provides the stability that allows life the billions of years of consistent conditions needed to evolve from simple cells to complex ecosystems. When we consider exoplanets, we must ask not just if they have water now, but if they have the geological machinery to maintain that water in a liquid state over astronomical timescales. A planet without plate tectonics might have a temporarily pleasant climate, but it would lack this long-term climate stability. Its atmosphere could slowly be depleted of CO2, leading to a permanent icehouse, or it could accumulate too much, leading to a Venus-like furnace. This adds another formidable filter to our search. We cannot directly observe plate tectonics on distant worlds yet, but we can look for indirect signs. A planet with significant and ongoing volcanic activity might be a good candidate, as volcanism is often a hallmark of an active interior and tectonic recycling. The composition of the atmosphere might also offer clues. An atmosphere with gases that are out of equilibrium could suggest geological processing. The carbon silicate cycle reminds us that a living planet is a dynamic planet with its solid, liquid, and gaseous parts all engaged in a slow, perpetual dance. It is a system that demonstrates resilience through change, constantly adjusting and rebalancing. Our existence is indebted to this hidden geological rhythm. As we scan the universe for other habitable worlds, we are ultimately searching for planets that are not just passively sitting in a habitable zone, but are actively maintaining their own habitability through processes like this. The silence from the cosmos might be explained in part by the absence of this planetary self-regulation on many worlds. They may have had water and warmth for a time, but without a thermostat. Their climates inevitably spiraled into irreversible extremes, leaving them forever silent, either frozen in time or burned to a cinder. The carbon silicate cycle is thus a key piece of the puzzle, a mechanism that transforms a merely potentially habitable world into one that can truly nurture life for eons. The intricate dance of planetary systems we have explored, from the carbon silicate cycle to the stabilizing influence of a moon, all rely on a fundamental and often overlooked planetary property: its rotation speed. How quickly a planet spins on its axis is not just about the length of its day. It is a critical factor influencing its protective magnetic field and the very patterns of its climate, both of which are essential for sustaining a habitable world. The connection between rotation and magnetic field lies in the dynamo effect, the process that generates a global magnetic field in the first place. This requires a planet to have a molten, electrically conductive core, typically iron, and that this liquid metal is in motion. The rotation of the planet provides the Coriolis force, which organises these convective motions into a coherent, planet-wide magnetic field. Think of it as a gigantic electrical generator powered by the planet's own spin. A faster rotation generally contributes to a stronger and more stable magnetic field. This magnetic shield is what deflects the charged particles of the stellar wind, preventing them from eroding the atmosphere over time. Now, consider a planet with a very slow rotation, like Venus. A day on Venus is longer than its year, taking 243 Earth days to complete a single rotation. This sluggish spin is thought to be a key reason why Venus lacks a strong, intrinsic global magnetic field. Without this protective shield, the solar wind interacts directly with the planet's upper atmosphere, ionizing atoms and molecules and allowing them to be swept away into space. While Venus has a thick atmosphere, it is likely that it has lost a significant amount of its original water and other light elements through this process over billions of years. The slow rotation fails to stir the core effectively, resulting in a weak or absent dynamo. Therefore, a planet's rotation speed can be a primary determinant of its ability to hold onto its atmosphere, the very blanket that regulates temperature and provides the chemicals for life. Beyond magnetic field generation, rotation profoundly influences climate and weather. A planet's spin creates the Coriolis effect, which deflects moving air and water, shaping global wind patterns and ocean currents. These currents are the planet's circulatory system, distributing heat from the equator towards the poles and helping to moderate temperature extremes. On Earth, our relatively rapid 24-hour rotation period fosters a dynamic atmosphere with complex weather systems, jet streams, and gyres that continuously mix the atmosphere and oceans. This mixing is vital for nutrient cycling, influencing everything from plankton blooms in the sea to rainfall patterns on land. Now, imagine a planet that rotates very slowly. Its day-night cycle would be extremely long. The hemisphere facing the star would bake for extended periods, becoming intensely hot, while the opposite hemisphere would radiate its heat away into the void of space, becoming profoundly cold. This extreme temperature difference would create ferocious winds howling from the hot side to the cold side. But these winds might be relatively simple in pattern, lacking the complex turbulence and storm systems driven by a faster spin. The climate could be locked into a rigid and extreme state, with a superheated day side and a frozen night side, making the Terminator line, the twilight zone, the only potentially habitable region. And even that would be subject to violent atmospheric shear. This scenario is particularly relevant for planets tidally locked to their stars, which is common in the habitable zones of red dwarfs. These worlds have a permanent day side and a permanent night side due to their synchronized rotation. While a thick atmosphere might help distribute some heat, the fundamental climatic challenge imposed by the lack of rotation remains. The absence of a day-night cycle would also have profound implications for life, affecting biological rhythms, photosynthesis, and weather patterns in ways we can barely imagine. Conversely, a planet that rotates extremely quickly would have very short days. This could lead to a more uniform global temperature, as no single region is exposed to stellar heating for too long. However, it might also generate incredibly powerful and constant wind patterns and potentially more severe storms. The magnetic field would likely be strong, but the rapid spin could also introduce other geophysical challenges, such as affecting the planet's shape or internal heat distribution. Earth's rotation speed appears to be in a beneficial middle ground. It is fast enough to generate a protective magnetic field and to create a dynamic, well-mixed climate system with distinct but manageable seasons and weather patterns. It is slow enough to allow for a stable day-night cycle that life has adapted to over billions of years. This Goldilocks zone of rotation speed is yet another subtle but critical parameter in the habitability equation. When we look at exoplanets, we cannot yet measure their rotation speeds directly for most cases, but we can infer possibilities based on their age and proximity to their star. Planets close to their stars are likely tidally locked, meaning their rotation speed is fixed to their orbital period. Older planets in general may have their rotation slowed by tidal interactions over time. A planet's rotation history is also important. A world might start with a fast spin, providing an early magnetic field, but slow down over time, potentially losing its protection just as life is beginning to get a foothold. The speed of rotation is thus a dynamic factor in a planet's life story. It influences the planet's ability to protect itself, to manage its climate, and to create the environmental rhythms that life may use as a clock. It is a fundamental piece of planetary mechanics that interacts with all the other systems we've discussed. A strong magnetic field requires a molten core and rotation. A stable climate requires an atmosphere, which requires a magnetic field, which in turn is aided by rotation. The interconnectedness is profound. As we add this filter to our list, the picture of a truly Earth-like world becomes even more precise. It is not enough to be the right size at the right distance. A planet must also have the right spin, a rhythm of rotation that fosters protection and promotes a temperate, mixed climate. The cosmic silence might be filled with worlds that are too slow, too fast, or completely locked, their potential for life stifled by a simple failure to turn at the right pace. So, the next time you experience a sunrise or feel the wind on your face, remember that these everyday phenomena are the result of our planet's specific and fortunate rotation, a spin rate that helps keep our world safe, stable, and alive. After exploring all these precise and intricate requirements for life as we know it, from magnetic fields to plate tectonics, we must confront a potentially limiting factor in our entire search, our own perspective. This is the problem of anthropocentric bias, the possibility that we are only looking for life that is fundamentally similar to us, based on carbon chemistry and dependent on liquid water, while the true diversity of life in the universe could be far stranger and completely beyond our current imagination. Our entire framework for habitability is built on a single data point, Earth. Every biosignature we search for, every condition we deem essential, is derived from the one example of life we have. This is a practical starting point, but it could be a profound blind spot. We look for planets in the habitable zone, where liquid water can exist because water is an incredible solvent, facilitating the chemical reactions of life. Carbon is the backbone of our biology because it can form 4 stable bonds, creating an unparalleled diversity of complex molecules. So, we search for other Earths, hoping to find a familiar signature in the cosmos. But what if life can be based on something else? Consider the element silicon, which is right below carbon on the periodic table and can also form 4 bonds. Science fiction has long played with the idea of silicon-based life, perhaps living at much higher temperatures where silicon-silicon bonds are more stable. On a hot, rocky world, perhaps complex silicon chains could form structures analogous to our proteins and DNA. However, there are significant hurdles. When carbon oxidizes, it becomes carbon dioxide, a gas that can be easily expelled by an organism. When silicon oxidizes, it becomes silica, sand, a solid that would be rather difficult for a living creature to dispose of. This doesn't make it impossible, but it suggests that silicon-based biochemistry would have to be very different, perhaps operating on much longer timescales or in environments with powerful forces to move solid waste. Perhaps a liquid other than water could act as the universal solvent for life. On an extremely cold world like Saturn's moon Titan, where surface temperatures hover around minus 290 degrees Fahrenheit, water is frozen solid as hard as rock, but rivers and lakes of liquid methane and ethane flow across its surface. Could a form of life exist there, using liquid hydrocarbons as its internal medium? The chemistry would be incredibly slow, and it would require a completely different set of molecular building blocks. But it is not entirely implausible from a chemical perspective. Instead of water-based cells, life might be based on lipid membranes in the methane seas. Instead of oxygen respiration, it might use another chemical process entirely. Ammonia is another potential solvent, liquid at a wider range of temperatures than water under pressure. A cold, high-pressure planet with ammonia oceans could, in theory, host biochemical reactions we haven't yet conceived. The problem is that our telescopes are not designed to look for the biosignatures of such life. If we point the James Webb Space Telescope at an exoplanet with a methane-based biosphere, we might see nothing of interest because we wouldn't know what molecules to look for. The atmospheric gases that would be in dramatic disequilibrium due to silicon-based life are a complete mystery to us. We are essentially searching for a specific kind of needle in a cosmic haystack, while ignoring the possibility that the haystack might also contain strange and wonderful pins, buttons, and other fasteners we've never seen before. This bias also extends to our concepts of intelligence and civilization. We assume that a technological species would use radio waves, build structures we can recognize, and perhaps even resemble us in some way. But intelligence could be so alien that we might not recognize it even if it were communicating with us directly. A sentient ocean, a collective consciousness of a fungal network, or a creature that perceives time in a radically different way might not have any interest in technology as we define it. Our search for extraterrestrial intelligence is, by its very nature, a search for a version of ourselves. This realization does not invalidate our current search, it simply frames it. Looking for a second Earth is a brilliant and logical strategy because we know for certain that life can work under those conditions. Finding one would be an epoch-making discovery. But we must also fund and encourage the science of alternative biochemistries to explore the true limits of life in labs here on Earth, subjecting extremophiles to ever more alien conditions and theorizing about what signatures truly novel life forms might produce. The universe, with its hundreds of billions of galaxies, is almost certainly more creative than we are. The elements carbon, hydrogen, oxygen, and nitrogen are common throughout the cosmos, so it is reasonable to assume that life, where it appears, might often use these abundant and versatile tools, but to assume it always will is a failure of imagination. The conditions for life as we know it are so specific that if they were the only path, the universe might indeed be mostly empty. But if we allow for the possibility of life as we don't know it, the number of potential habitats explodes. Frozen worlds, hot worlds, gas giants, and even the cold, dark interstellar space could, in theory, host some form of chemistry complex, enough to be called life. This makes the search simultaneously more hopeful and more difficult. It is more hopeful because life could be almost anywhere. It is more difficult because we don't know what to look for, and we may have already collected data containing evidence of alien life, but dismissed it because it didn't match our template. As we move forward, the greatest tool in our astrobiological toolkit may be open-mindedness. We must be prepared for the familiar, but we must also build the capacity to recognize the strange. The first sign of extraterrestrial life may not be a radio signal or a plume of oxygen, but a bizarre atmospheric cocktail of chemicals that makes no sense to our current models of planetary geology. A pattern that whispers of a biology operating under rules we have yet to decipher. The final frontier in the search for habitable planets may not be in the stars themselves, but in our own minds, in our ability to let go of our Earth-centric assumptions and embrace the truly alien possibilities that the cosmos holds. This is the ultimate challenge, to find life. We must first understand how little we truly know about what life is. The silence from the cosmos might not be a silence of absence, but a silence of misunderstanding. We are listening for a voice like our own in a universe that may be full of songs we cannot yet hear, composed in keys we cannot yet play. So, as we continue this grand quest, we do so with both the precision of a scientist and the wonder of a child, always asking, what if? And never assuming that the only life that counts is the kind that looks back at us from the mirror.